OpenCV is a popular Python library for real-time computer vision. This course comes directly from the creators of OpenCV and is the perfect course for beginners. At the end of the course, there's an interview with the CEO of OpenCV, Dr. Malik, and he talks to you about how to get a job in computer vision and AI.
In 2005, for the first time in human history, an autonomous vehicle traveled 132 miles through the Mojave Desert to win the $2 million DARPA Grand Challenge. The name of the car was Stanley, and it used a computer vision library called OpenCV. Hello everybody, I'm Satya Malik, and I'm thrilled to help you get started with OpenCV. Built over 20 years, OpenCV is the most extensive computer vision library in the world. It is downloaded between 1 to 2 million times a week, and it contains over 2,500 optimized algorithms. To build computer vision and AI applications, OpenCV is the first library you need to learn. Welcome to this free Getting Started series. We designed it for absolute beginners. All you need is an intermediate level of programming knowledge in Python. OpenCV is vast. It is not possible to cover all aspects of the library in this short period of time. This series is your first step. It will help you get started. The material in the series will be covered using Jupyter notebooks. We will go over every notebook in a video to help you understand the code. The first few notebooks are all about basics. What are images and videos? How do we represent them inside OpenCV? What OpenCV functions do we use to read, write, and manipulate photos and videos? Next, we will go over image enhancement and filtering. Our objective in this series is also to give you a glimpse into applications you can build using OpenCV functions. We will go over different image transformations and show you how to align two images. The same idea can be modified slightly to create beautiful panoramas. Next, we will dip our toes into computational photography and create high dynamic range images by combining photos taken using different exposures into one single beautifully lit photo. OpenCV also implements many classical machine learning algorithms and has an entire module dedicated to deep learning inference. We will learn how to implement face detection and object tracking. Finally, we will wrap up the series by learning how to use deep learning module for object detection and pose estimation. It's going to be very interesting. That's all we will cover in this Getting Started series. And after completing this series, I encourage you to go and take a look at the free content at opencv.org and learnopencv.com. And when you're ready for structured learning and you're seeking mastery in computer vision and AI, check out our courses at opencv.org/courses. I wish you all the best in your learning path. But today, let's get started with OpenCV.
Hi everyone, in this introductory video we're going to be covering several basic image processing concepts related to working with images. All this material is very essential, and we'll be using Python and specifically OpenCV to demonstrate, for example, how to read an image and display it, understanding how images are represented by data, the differences between grayscale images and color images, and specifically what it means to have multiple channels in color images, and then finally how to save images. So just a couple of things I wanted to mention before we get started is that we'll be using Jupyter notebooks for most of these demonstrations, mainly because it's a very convenient way to display intermediate results and has some very nice documentation features that make it easy to present code and supporting material. So in some cases we might actually use Python scripts for specific applications, but mainly we'll be using Jupyter notebooks in this series. So to get started, I just wanted to talk a little bit about this first section here where we're importing some required libraries. One thing I wanted to mention is that when you use Jupyter notebooks, you want to use this matplotlib inline specification here so that we can display images directly in the notebook. And then one other thing that we'll be using in this notebook is this IPython function image, which will allow us to display and render images directly in the notebook. So in this first example here below, we're going to actually use that function to display two checkerboard images here. They're both black and white checkerboard images. And the first one here is 18 by 18 pixels, and this next one here is 84 pixels by 84 pixels. And you can see that if we read in those files and display them directly in the notebook, that their actual size is faithfully rendered. So the 18 by 18 pixel image is quite small here, and you can see the difference between the two images. And one of the reasons we wanted to start with that is because generally we'll be using OpenCV to actually read in an image and store that data in memory as a NumPy array, and then working with that NumPy array in terms of manipulating the image or saving the image or displaying the image. And in those cases, we're really displaying a mathematical representation of the image and not necessarily a faithful representation of the image within the browser itself. So that'll become more clear as we proceed further through this notebook, but we just wanted to draw that distinction. So let's scroll down here and take a look at the first function that we're going to be using from OpenCV. Before we get started, though, I just wanted to mention that when we introduce new functions, we decided to include this documentation section here in the notebooks that summarize the functional syntax, describes some information about the arguments required, maybe some optional arguments, and then we've also provided the OpenCV documentation links. So we're not going to go through these sections in great detail, but we will refer to them when we describe some of the code in these notebooks. So let's just take a look at how we use IamRead. And in this first example here, we're reading in the smaller checkerboard image. Notice that the first argument is just the file name for the image itself, which can be either a relative or an absolute path name. And notice also there's actually an optional second argument here, and here we're indicating 0. And if you look back up here in the documentation section, you'll see that 0 corresponds to a flag that specifies that we want to read this image in as a grayscale image. And we'll talk more about this further below, but I just wanted to point out that there is an optional second flag here that we'll make use of quite a bit. And then the return from IamRead is a NumPy 2D array representing the image. And I can print that information here using the print command, and you'll see down here there is the data that represents that image. So it's 18 rows and 18 columns, and each of the values represents the pixel intensities for each of those pixels. And notice that they're in the range of 0 to 255 because this image is being represented by an unsigned 8-bit integer. So let's scroll down here a bit further and print some information associated with the image. So drawing your attention up here to this code block, we're using the shape and dtype methods of that NumPy array object to print out both the image size and the data type. So here you can see it's 18 by 18 and unsigned int, as we had pointed out. And so at this point, let's talk about how to display the image. So here in this code block, we're using the matplotlib function IamShow to display a representation of that image. And so here we're just passing it the NumPy array that represents that image. And you'll see this plot below. So notice that this is actually a plot or a mathematical representation of that image, but it's not 18 pixels wide on my screen. It's just a plot representing 18 pixels, and so you can see the axes here correspond to 18 by 18. Also notice that it's not black and white as we expected, but looks like yellow and dark navy blue. And the reason for that is that matplotlib uses color maps to represent image data, and in this particular case it's using some other color map rather than a grayscale color map. So if we want to display this as an actual grayscale image, we need to actually set the color map. So we're going to do that here in this section where we call IamShow with an optional argument, color map equals gray. And if we set the color map equal to gray, then we get what we expected, a black and white image representation. So let's take a look at another example. Here we're reading in another checkerboard image of the same size, but this has pixel intensities that range from 0 to 255 with lots of gray values in between. So you can see that reflected here in the matrix itself. And then when we plot the image, you can see the grayscale representation of those middle tone values. So it's not a very interesting image, but it demonstrates just the idea that a grayscale image can have values between 0 and 255, and that those are represented on a continuum from pure black to pure white. So now we're ready to talk about color images. So let's scroll down to this next section here where we're going to read in a high resolution image of the Coca-Cola logo. So here we're using the IPython image function to do that, and we're rendering that image in the browser. And let's scroll down to this next section now and actually use OpenCV IMRead to read that in and store that data in a matrix. So here we're storing that information in this Coke_image object. Notice that when we read it in, we specified an optional second argument of 1 here. So it's going to read in this image as a color image. And it turns out this image is in an RGB format. So there's 3 channels, one for red, green, and blue. And when we print out the size and the data type of this matrix, you can see it's 700 by 700 by 3, where 3 is the number of channels. But notice that when we display the image down here using matplotlib imshow, it comes up blue, which is unexpected. And the reason for that is because OpenCV actually uses a different format for storing the channel information than most other applications. So for RGB images, OpenCV uses a channel order of BGR rather than RGB. So matplotlib is expecting this to be RGB, but the way that OpenCV read this into the matrix, it stores it in BGR, so it ends up looking blue unless we swap the order of the channels. So that's what this next bit of code down here does. In this block here, we're taking this Coke image array and swapping the order of the channels here. That's what this syntax does here. It reverses the order of that last member of the array. And now we're going to display that, and it comes up red and white as we expected. So that's just something to be aware of. Whenever you're working with OpenCV, you need to be aware of the channel order convention, and we'll see that come up again and again in these notebooks. So now we're going to take a look at splitting and merging color channels in this next section here. Splitting and merging are pretty straightforward in OpenCV, and you can refer to this documentation link for more details. But here's the example, so let's just go over that. Here on this first line, we're using IMRead to read in a color image. And notice here for the optional argument, we're actually specifying the flag as opposed to 1 for specifying that we want to read this in as a color image. And we're going to store that result in image_nz_bgr. And I specifically used BGR in the name of the variable to remind myself that that's what this represents, since we're reading it in using OpenCV. And now on this next line, I'm going to call the OpenCV split function to take that multi-channel image and split it into its components B, G, and R. And so each of these variables represent a 2D NumPy array that contain the pixel intensities for those color channels. So in this next section of code here, we're simply going to use imshow to display each of those representations as a grayscale map. And then this last bit of code here takes those individual channels and uses the merge function to merge them back into what should be the original image. And we'll call that image merged here, and we'll show that as well. So now taking a look at the images below, we've got the red, green, and blue grayscale representation of each of the channels, and then the merged output over here to the right. And it's worth a little bit of a mention here, but you can get some intuition by just taking a look at the original image. So for example, this lake is kind of a turquoise blue, if you will. It's got some green and blue in it for sure, and probably very little red. So if you now go back to these channels, you can see that the red channel for the portion of the lake is low, meaning there's not much red component in that color. So that's why it's darker. It's closer to 0. And notice that the green and the blue channels are fairly high intensity for their respective colors. So that's indicating that the color of that water there has very little red in it, but quite a bit of green and definitely quite a bit of blue. So that's kind of the interpretation. So next, let's scroll down here and talk about another function in OpenCV called CVT color. This allows you to essentially convert between color spaces. So the syntax here is you supply a source image and a code indicating the type of conversion you want, and the result will be a different color space. So this is easiest to talk about just with an example. So we have a very simple example here, converting from BGR to RGB. So we're calling CVT color, and we're passing it the BGR representation of that image that we read in above, and we're specifying a code of BGR to RGB. So this is simply a flag indicating to OpenCV that we're supplying it a BGR image and we want to convert it to RGB. And so I'm storing that here in this new variable, and then I'm going to use IMShow to display that, and this is what we expect. We're just simply displaying the original image. But if you look at the documentation for CVT color, you'll see that there's all kinds of color codes that allow you to convert between color spaces. And so that's the subject of this next section of the notebook here, where we are going to convert that image to a different color space. So in this first line up here, we're going to convert the BGR representation of that image to an HSV representation. So HSV stands for hue, saturation, and value, and that's another color space that's often used in image processing and computer vision. And so we're going to store that result in a variable named image underscore HSV. So now I can split those channels just like we did above and get the H, S, and V components. And just like the example above, I'm going to plot all four images here, the three channels and then the original image. For example, hue represents the color of the image, saturation represents the intensity of the color, and V represents the value. So you can think of saturation as being a pure red versus a dull red, and you can think of value as being how light or dark the color is, irrespective of the color itself. And then hue is more like the representation of the actual color. So just as an example, in this next section here, we're going to actually modify one of the channels. So if you look at this first line of code here, I'm going to take the current hue value and add 10 to it. So we're just shifting where we are on the color spectrum. And then I'm going to merge that new channel with the original S and V channels and get a merged image. And then I'm going to use a CVT color to convert that from HSV to RGB. So now I've modified one of the channels, I've merged it, and now I've converted it. And then I'm going to use IMShow below to display each of the color channels and then the modified merged image. So you can see here that the modified image, because we've changed the hue, looks different from the original image up here. So that's a brief introduction to color channels and color spaces, and now we're ready to move on with the final section of this notebook, having to do with saving images and writing them to disk. So there's a function in OpenCV similar to IMRead. It's called IMWrite, and it's very simple to use. You simply pass in the file name that you want to save the file as, and then the image itself. And so there's an example here. We're going to use the IMWrite function, and we're going to give it a file name New Zealand Lake _ saved to indicate that we're actually saving this from our notebook. And we're passing it this image that we've been working with here in BGR format. And then on the very next line here, we're going to use that IPython image function to read that file back in and render it right here in the browser. And then the last thing we wanted to conclude with is just taking this image and using IMRead to read it in, both as a color image here and as a grayscaled image here, and then print out both of those arrays. And notice that the first one read in as a color image has got 3 channels, and the one that's read in as grayscale has got just the single channel. So we did cover quite a bit of material in this notebook, and we hope it's been a good reference for you. There is one other thing that we'd like to discuss, but not from within the notebook. So we're going to move over to a development environment and spend just a few minutes talking about the differences between Matplotlib IMShow and OpenCV IMShow. So we'll continue on there in just a second. Okay, so here we are in the development environment, and we put this script together so that we could demonstrate some of the differences between the Matplotlib version of IMShow and the OpenCV version of IMShow. And we start by just reading in 2 colored images. This first one here is a colored checkerboard image, and then the second one here is the Coca-Cola logo. And then this very first block of code here is using the Matplotlib version of IMShow to display the checkerboard image. And we've seen examples of that before in the notebook. The rest of this code is all centered around using the OpenCV version of IMShow. And there's some extra code here that's required in order to use this properly. So the first thing we do is create a named window here, and then we call the OpenCV version of IMShow, passing it the named window and then the image we want to display in the window. And notice right after this we call a wait key function. And the argument to that function is the number of milliseconds that this window will be displayed. So 8 seconds in this case. If we didn't call this wait key function, then the IMShow function would display the window indefinitely and there'd be no way to actually exit the window. So the wait key function is meant to be used in conjunction with the IMShow function. So then we're going to continue on and perform the same set of actions except with a different image, the Coke image in this case, just so you can see the dynamic behavior. And then finally down here in this third section, we're going to do the same thing, displaying the checkerboard image again, but this time we're going to pass a 0 to the wait key function. So rather than displaying the image for 8 seconds, 0 means it'll be displayed indefinitely unless any key on the keyboard is struck. So this allows you to have user input rather than waiting for a specific time to pass. And then there's one other option down here that you could use in conjunction with a while loop. You could call the IMShow function inside of a while loop and then monitor the keyboard to only exit the loop if the user types a specific key, like for example the lowercase q to quit. So let's take a look at how this behaves when we run the demonstration. So here we're displaying the image using matplotlib, and I can go ahead and exit that window. And now this checkerboard image is going to be displayed using the OpenCV version of IMShow, but only for 8 seconds. And then the same with the Coca-Cola logo. And notice that I'm not able to actually exit the window. I have to wait the 8 seconds. And now we're back to the checkerboard image, but in this case, we passed a 0 to the wait key function. So this is just going to be displayed indefinitely until I hit a key on the keyboard. So I'll go ahead and hit the space bar and this will disappear. And now we're in the while loop and the Coca-Cola image is being displayed. And if I hit the space bar, nothing happens because the wait key function is being monitored for the user to type a lowercase q. So lowercase q is going to be the only key that will allow this to actually exit. So I'll go ahead and hit the lowercase q. And so that's another way for you to use the OpenCV version of IMShow. So we hope that gives you a better feel for some of the subtleties associated with using the OpenCV version of IMShow. And that's all we wanted to cover in this section. In this video, we're going to be talking about basic techniques for manipulating images, which include changing the values of individual pixels within an image, as well as some other useful transformations like cropping, resizing, and flipping images. These are all very standard transformations and very easy with the help of OpenCV functions. So let's get started and take a look at the first example below here where we're going to manipulate individual pixels. This is the image that we worked with in the first video. It's the black and white checkerboard that's 18 pixels wide and 18 pixels tall. So let's scroll down here a bit further and talk about how to access individual pixels within this image. So let's suppose we wanted to access this very first pixel in the first black box and then this very first white pixel in that box. That would correspond to this element up here, 0, and this first element here, 255. So the first thing we need to mention with regard to accessing these elements is that NumPy's arrays are 0-based. And so if we just draw your attention down here to this code, we're going to print out the cell associated with the first column in the first row. So that would be the 0, 0 pixel, and that would be this 0 right up here. And then this next print statement is going to print out the pixel associated with the first row and the 7th column. So that's 1, 2, 3, 4, 5, 6, 7, but we give it an index of 6 because it's 0-based. So if you take a look at the printout, you get the 0 and 255. So that's printing out the value of this pixel here and this pixel here. So now let's scroll down a little bit further and see how we actually modify pixels. So in this next code block here, we're going to make a copy of the image just so we can modify it and still retain the original image for reference. So here we're going to modify the value of 4 specific pixels indicated by these 4 assignments here from the 2, 2 entry to the 3, 3 entry. So that would actually correspond to the 3rd row and 3rd column and 4th row and 4th column, those 4 pixels right there. So we're going to set those to 200. This could also be accomplished by NumPy slicing notation. So that would just be 2 to 3, comma 2 to 3, as opposed to setting all 4 of these assignments. But in either case, if we display the image, you can see the modified pixels here in the matrix, and then of course if you display the image, then you can see that these have been set now to a light gray tone here in the center. So it's very simple to modify individual pixels, and we just want to give you a brief demonstration of that. The next topic that we're going to cover here is cropping. So cropping is similar in some sense to what we described above because it involves array indexing. So let's take a look at this example here. We're reading in a color image of this boat in the water, and we're specifying, of course, that this is to be read in as a color image here. And we're storing that as a BGR format. And then the first thing we're going to do is swap the color channels on that, as we've indicated before, and then display the image using matplotlib imshow. So there's the image. And now suppose we're interested in cropping out the small area around this boat. So let's say from rows 200 to 400 and columns 300 to 600. Well, the way that we would do that is simply index into the original array here, rows 200 to 400 and columns 300 to 600, and then reassign those values to this new variable called cropped region. And if we plot that cropped region, you can see that's what we get. So cropping is very simple and straightforward. It's simply indexing into an existing image and extracting the region that you're interested in. So now let's move on to the next section, which is resizing. And for this purpose, we're going to use the OpenCV function resize. And it takes several arguments. So there's 2 required arguments. The first one is the source image, and the second required argument is the desired output size of the image. And then there's several optional arguments here, and specifically fx and fy, which are scale factors, which we're going to demonstrate below. And then there's this interpolation method. And we're not going to go into those details, but just know that there's several interpolation methods that you can select from. For example, when you're resizing an image up, you're having to invent new pixels, and therefore there's an interpolation that's required to do that. So let's take a look at an example down here. In this first method, we're going to use the scaling factors fx and fy. And so here's the call to the resize function. So we're passing it the cropped image. And then for the second argument, since that's required, we have to specify it, but it's okay if you specify it as none. And now that allows us to instead use these scaling factors fx and fy. And in this example, we're just going to set those to 2. So we're going to double the size of this cropped region, and you can see that when we display the result, that's exactly what we get. This is now 400 pixels high and 600 pixels wide. So now let's talk about another method for resizing images. In this method, we're going to set a specific width and height for the image. So in this case, 100 and 200. And we're going to create this 2-dimensional vector here indicating both of those dimensions, and pass that as a second argument to the resize function, and display the resized cropped region. And in this case, we get exactly what we asked for, 100 wide and 200 high. But of course, the image has been distorted now because we didn't maintain the original aspect ratio of the image. So that leads us to the last method here, which is still using this dimension vector here. But we're going to start by specifying a width of 100 and then calculate the associated desired height while maintaining the aspect ratio. So here we're creating this ratio of the desired width to the original width of the image, and then using that factor to derive the desired height here. And so now when we pass that revised dimension to the resize function, you see that we get an image here that 100 pixels wide and the appropriate amount high to maintain the proper relationship, which turns out to be about 67 pixels. And then further here below, we're going to go ahead and write these images to disk and then read them in. So this is the cropped region that's been resized by a factor of 2. And we're going to swap the channels on that here, and then write that to disk and save it as this file name here. And then read it back in and display it directly in the browser. So you can see how large it is here. And then we'll also perform the same operation on the cropped region prior to resizing and display that, and you can see that it's half the size as the one that we resized. So that's all there is to resizing. It's fairly straightforward, and now we're going to move on to image flipping. And the function we'll be using is flip, and it simply takes the image itself as the first argument, and then a flip code which specifies how we want to flip the image. And there's three options for that. You can flip it horizontally, vertically, or in both directions. And those are simply specified by 1, 0, and -1. And so let's take a look at an example here. Here we're passing in the original image, and we're making three function calls corresponding to the three options here for flipping, and we're simply displaying them down here below. So this first one here has been flipped horizontally, this one's been flipped vertically, and this one's been flipped around both axes. And then finally, this is the original here. So that's all we wanted to cover in this section, and thank you, and we'll see you next time. In this video, we're going to describe for you how to annotate images with lines, circles, rectangles, and text. Keep in mind that this also applies to video frames, and so that can be very helpful as well. So to get started, we're going to read in an image here, and we've got it displayed here in the browser, and we'll be working with this image for the rest of the notebook. But one thing I wanted to point out is that notice that even though this may have been a grayscale image, we're actually reading it in as color, and we're doing that because we want to demonstrate annotations in color. So we'll need to have a color image to work with, or a color representation at least. And so let's proceed down to the first section here, where we're going to learn about how to draw a line on an image. The OpenCV functions that allow you to annotate images are all very straightforward. And in this case, the first argument here is the image itself. And then the next two arguments are the first point and last point of the line, and then the color. So those are the four required arguments. And then there's some optional arguments that we'll specifically take a look at as well, including thickness and line type. So let's scroll down here to the first example. So here we're making a copy of the image simply so we can preserve the original image and then annotate a copy. So this one's called image line. And we're going to draw a line on this image. You can already see it's a yellow line, and we're going to draw it from point 1 to point 2. So that's 200 along the x-axis and 100 along the y-axis. That's this point here. And then 400 along the x-axis and 100 along the y-axis. So that's this point here. And then we're going to specify yellow. And recall that this has to be in BGR, not RGB, and that's the reason that the last two channels here are 255 to produce yellow from red and green. And then line thickness of 5. And then for the line type, we're using this line underscore AA, which stands for anti-aliased. And that's usually a good choice. It uses semi-transparent pixels and often produces a very smooth and nice looking result. So that's the first example. The remaining examples will be very similar to this with just some minor variations. So let's take a look at how to render a circle on an image. In this case, we have to specify the center and radius of the circle here, but everything else is the same in the argument list. So scrolling down to this example, you see we're going to render a circle here at the coordinate 900, 500. So that's 900 along the x-axis and 500 down, and then with a radius of 100. So moving on to rectangles. Again, there's four required arguments, but in this case, point 1 and point 2 refer to the top left corner of the rectangle and the bottom right corner of the rectangle. But again, all the other arguments are the same, and the specifications are all the same. So in this case, we're going to draw a rectangle around this launch tower here. The upper left corner of the rectangle is at 500, 100, which you can see here. And then the lower right is 700, 600, which is right here. And we're going to specify a different color for that. And then finally, moving on to text. Text is a little bit different. There's obviously some additional arguments. The first argument here is the text string. The next argument is the origin of the text, and that refers to the bottom left corner of the text string, where that's going to be placed on the image. And then the font face, you might also think of that as the font style. And then font scale is a floating point number that scales the font size. And then again, we have some optional arguments here. So just taking a look at this example here, we're setting several of the arguments right here. So the text string is here. We're setting a font scale of 2.3. The font face is font Hershey plain. If you go to the documentation link here, you can find out what font faces are available, and I just selected this one. And then the font color is going to be bright green, and the font thickness of 2. And then I've got the origin right here for the text string, so that's 200, 700, so that's just right here at the lower left-hand base of that text string. So that's really it. Annotations using OpenCV are very straightforward and simple, and that's all we wanted to cover in this section, and we'll see you next time. In this video, we're going to be covering several different basic image processing techniques used for both image enhancement as well as upstream pre-processing functions that are often used for many different applications. We'll be covering quite a few topics, including arithmetic operations, thresholding and masking, and also bitwise operations. All of these are very fundamental to many computer vision processing pipelines, and we've also included a couple of different application examples so you can get a better feel for just how these techniques can be used in practice. So with that, let's scroll down here and take a look at our first example. Here we're reading in a color image and displaying it right here within the browser. And what we'd like to do is adjust the brightness of this image. So let's take a look at how we can do that. So in this section here, we're displaying the original image here in the center, and then we've adjusted the brightness of the image both darker to the left and brighter to the right. And so let's take a look at the code that accomplishes that. So we start here in the first line by creating this matrix, and we use the NumPy ones method to do that, and we're going to pass in the shape of the original image here, and then also the data type, which is unsigned 8-bit. And we're going to multiply that by 50. So now the result of that is a matrix that's the same size as the original image, and it's got pixel intensities of 50 everywhere in the image. And so now we're simply going to use the OpenCV add and subtract functions to add and subtract that matrix from the original image, and then we're simply going to display those. So that's all that's required to generate an image that's darker than the original and an image that's lighter than the original. So now let's talk about how to change the contrast in an image, and that's a little bit different because contrast is defined as the difference in intensity values of the pixels within an image, and so that's going to require a multiplication operation. So we start here by creating two matrices, and each of these is going to use the NumPy ones function and create a matrix the same size as the original image. And in both cases, we're going to multiply those matrices by a factor. So in this first case, it's a factor of 0.8, and in the next case, it's a factor of 1.2. So now these matrices contain floating point values that have been scaled by these two factors here. And on these next two lines, we're going to multiply those matrices by the original image. But note that there's a nesting here that's required. So the two matrices we defined above contain floating point values. So in order to multiply those by the original image, which was unsigned int, we're going to first convert those to float and then do the multiplication here using the OpenCV multiply function. And then after that, we're going to convert those back to unsigned int 8-bit. And so now we have those results here in these two variables, and we're simply going to display those, and you can see the results below. The original image is in the center here, the lower contrast image to the left, and the higher contrast image to the right. So you'll notice here that in the on the right-hand image there is this odd color coding in here. Something's gone wrong. And the reason for that is because when we multiply the original image by this matrix that has a factor of 1.2 in it, we potentially get values that are greater than 255. So if you look at the original image here, these clouds here were probably close to 255, some of them at least, and when we multiplied by 1.2, we exceeded 255. So then when we attempt to convert those values to an unsigned 8-bit number, rather than exceeding 255, they just roll over to some small number, and that's why these intensity values are now close to 0. And so that's the reason for the issue here. So let's take a look at how do we remedy that. So if we scroll down to this next section and take a look at that line of code here, what we can do is use the NumPy clip function to first clip those values to the range 0 to 255 before converting them to unsigned 8-bit. And now when you look at the right-hand image, it looks fine. And in fact, this portion of the image here has been completely saturated. So some of these values here are right at 255. So they have really no information. They're the extreme highlights within the image. So that's a summary of brightness adjustment and also contrast adjustment. So let's continue on to the next section of the notebook, which covers image thresholding. Thresholding is a very important technique that is often used to create binary images that allow you to selectively modify portions of an image while leaving other portions intact. And we have a couple of examples below to demonstrate this, but first just wanted to point out a few notes here in the documentation. Notice that we're specifying two different functions here, threshold and adaptive threshold. So just taking a look at the threshold function here to see how this works. It takes as input a source image and then a threshold value between 0 and 255, and then a max value for the binary map, and then a type of thresholding that we're going to perform. And in all of our examples below, we're going to be using a binary threshold. So the idea here is that whatever threshold you specify, pixels in the original image that are below this threshold will be set to 0, and pixels that are above that threshold will be set to 255. And so the result will be a binary map that contains either zeros or intensity values of 255, or whatever you had set the max value here to, which is typically 255. So let's take a look at the adaptive threshold function. It also takes a source image, a maximum value for the binary map, and then a method type to perform the adaptive thresholding, and also a threshold type, which is the same type of input as we had up here in the first function. And then also a block size and a constant value here. Both of these are used by the adaptive method algorithm. Basically, the block size is an indication of the pixel area that's considered when computing the adaptive threshold spatially across the image. So there's a lot of detail in here, and we simply wanted to include this for reference and then to show you some examples below. So let's take a look at the first example here. So here we're reading in an image, which is a photograph of a building with lots of windows and a geometric structure. And we're going to call the threshold function and pass it that image, and then give it a threshold of 100 with a max value of 255, and then specify this flag here to indicate that we want a binary map. And what's returned from this function is the binary image. This return value here is not important at this point, so it's this argument here that contains the actual binary map. And so we're simply going to display that below, both the original and the thresholded image. And you can see that there's an opportunity here for you to use this map as a way to selectively process certain parts of the image. So let's take a look at a more concrete example down here below. Suppose you were interested in building an application that could read and decode sheet music, which is very similar to optical character recognition, where the goal is to recognize characters in text documents. In this case, you'd be trying to recognize musical notes for the purpose of digitizing that information. So in the example below, it's easiest to actually start off with talking about these two images here, and then we'll come back up and talk about the code. So over here on the left is the original photograph of some sheet music, and you can see that it's kind of dark here in the lower right-hand corner. Clearly not a white background, but the notes are fairly well defined. They're all very dark black, which looks good. And the idea here is that we'd like to perform thresholding on this image to achieve a binary map, similar to the one shown here to the right. So just taking a look at the dark values of all these notes in the musical notation, it looks like perhaps the intensity values of all these black areas might be below 50, for example. They all look pretty black. Even some of these up in here look fairly black. So if we create a binary map with a threshold of 50, we're hoping that we would be able to isolate all of this important information. And the image to the right here was actually produced with a threshold of 50. And the result is rather surprising because notice that there's no information up here in the top portion of the image. That would mean that the intensity values of all these black notes are actually above 50, which isn't very intuitive because they look rather dark. So that's just one example. So let's go back up here and take a look at the code that produces these plots. So here we're just reading in the original image here, and then we're going to call the threshold function, passing it the original image, a threshold of 50, a max value of 255, and then a flag here indicating that we want to produce a binary map. And so what we get back here is the thresholded image, and this is what is actually displayed down here to the right. But there's some additional code here. So there's another thresholding call here, and this time we're going to pass it a higher threshold of 130 with the hopes that we can extract more of this information up here on the top of the image. And then finally, we're going to call the adaptive thresholding function and specify the type of thresholding algorithm and the fact that we want to create a binary map, and then some settings here for the algorithm. And then we're going to display all four of these below. So you can see the first two here that we've already talked about, but let's scroll down here and see the next two. So you can see that the one at the lower left here that was produced with the global threshold of 130 did a better job of isolating the musical notes here in the top portion of the page, but that threshold was far too high in order to accommodate the lower portion of the page. So what's going on there is that these dark values on the page, this shadow essentially, is actually lower than 130. So as a result, this whole portion of the page is just blacked out. So neither of these global thresholds, 50 or 130, do a very good job. And you could actually experiment with other thresholds and find out that there's not going to be a single global threshold that's going to do very well in this situation. So notice that the plot at the lower right here that was produced using adaptive thresholding is much better. This is a very good example of how you can take an image that's pretty challenging and has several dark areas here and actually isolate just about everything you want to in the image. So we simply wanted to point out the importance of thresholding, and in particular adaptive thresholding. And so now let's move on to the next section of the notebook, which covers bitwise operations. So here in the documentation section, you can see that we have four different functions: bitwise AND, OR, XOR, and NOT. And here we're showing an example of the bitwise AND. It takes two input images. These can actually be the same image, but they don't have to be. And then it takes an optional mask. And the mask specifies which portion of these two images the logical operation applies to. So let's take a look at this example down here. We're reading in two different images. These are both grayscale binary images that we're going to perform these operations on. And let's just see how that works. So we'll start with the bitwise AND operator here. So in this case, we're passing in the image of the rectangle and the image of the circle, and then we're indicating the mask is none. So we're simply going to do a bitwise AND comparison between these two images, and the value returned from that comparison will be 255, or white, if the corresponding pixels in both images are white. So in this case, the result will be just this left side of this half circle, since that's the only region in both images where the pixels are white. So now let's take a look at the bitwise OR operation. In this case, the return value from the operation will be white if the corresponding pixel from either image is white. And so in that case, we get the entire left side of the rectangle, which is white, and then the right-hand side of the circle. So now let's take a look at the XOR operator. And in this case, we're passing it the same set of arguments. The operation is simply different. And the exclusive OR works as follows. It'll only return a value of white if either corresponding pixel is white, but not both. So this is the result that you get here. So that's a summary of those three functions. So now let's take a look at an application using bitwise operations and binary maps. So in this example here, we're interested in manipulating this Coca-Cola logo. And we're going to start with the logo and also what we call a background image here, this colorful checkerboard. And we'd like to achieve this result to the right. So essentially being able to display a background image behind the white lettering and have it show through. So that's the goal, and we're going to go ahead and proceed through this notebook to see how that's done. So first down here, we're going to read in what we call the foreground image, which is the Coca-Cola logo itself. And we're going to display that in the browser here. And then further down here, we're going to do the same thing with the background image. In this case, there's a little bit of extra code up here in order to make sure that that image is the exact same size as the Coca-Cola logo. So as we've seen before in a previous video, we're making use of the OpenCV resize function here to accomplish that. So now we're going to go ahead and create a couple of masks from the Coca-Cola logo. So in this top portion here, we're going to pass in the logo here to CVT color, convert it to gray, and then use the OpenCV threshold function to create a binary mask from this grayscale image, and we're going to call that image underscore mask, and we're displaying that down here. So this is only going to contain values of 0 and 255. And then we're going to perform a similar operation down here, but not using the threshold function, although we could have. We could have used the threshold function down here and specified a threshold binary inverse mask, but instead we can just simply call the bitwise not function on the image mask to return the inverse mask. And so you see both of these masks displayed here in the browser. Now we're going to make use of those down here below. So now in this section, we're going to do a bitwise AND on the background image with itself, but using the image mask. So this bitwise AND operation is going to perform a bitwise AND between the corresponding pixels between these two images, which is the same image, but it's only going to apply it to the mask, which is the white lettering in this case. And so that's the result we get. Everything else is going to be 0, and we're going to get just the colors showing through in the logo. And then we need to do a similar operation on the logo itself, which is image underscore RGB, and we're going to do a bitwise AND operation on that and pass it the inverse mask, and that's going to allow us to only show the red foreground, and everything else is going to be black. And so now you can see that if you just added these two images together, the blacks sum to 0, and what you get is the following result. So we thought that was an interesting way to demonstrate how you could use binary maps and thresholding and logical operations to accomplish something like this. So we covered a lot of material in this video, and just keep in mind that all of this is very fundamental to many different image processing and computer vision pipelines, and we'll continue on in this course with a little more focus on actual applications now that we have some of this basic material under our belts. So thank you, and we'll see you next time. In this video, we're going to be describing for you how to access the camera attached to your computer system and send that streaming video to an output window on your display. So we have a short script here that accomplishes that, and we'll walk through this, and then we'll go ahead and execute it so you can see it in action. So starting on lines 35 and 36, we're importing OpenCV and the systems module, both of which are required below. And then on line 38, we're specifying a default camera device index of 0. On line 39 and 40, we're simply checking to see if there was a command line specification to override that default value. But in this case, we're just going to use 0. And then on line 42, we're going to call the video capture class to create a video capture object, and we pass in device index into that class. So device index of 0 will access the default camera on your system. If you had more than one camera attached to your system, then you would need to indicate a device index that points to the correct one. So 0 would be the default, 1 would be the second camera, 2 would be the third camera, and so forth. On line 44 and 45, we're creating a named window which we're going to eventually send the streamed output to. And then finally on line 47, we're going to create a while loop. And this while loop is going to allow us to continuously stream video from the camera and send it to the output unless the user hits the escape key. So that's what this wait key function does. It continuously checks whether or not the users hit the escape key. So the first line in this loop, line 48, uses that video capture object source to call the read method in that class, and that read method will return a single frame from the video stream as well as a logical variable has underscore frame. So if there's any kind of a problem with reading the video stream or accessing the camera, then has frame would be false, and we would break from the loop. Otherwise, we'd continue on and call the IM show function in OpenCV to actually send the video frame to the output window. So that's all there is to it. There's not much code. We just wanted to walk through that and give you an example of how to do this. So let's go ahead and execute it. And there it is. Here's the window streaming video from my web camera right to the display. As soon as I hit the escape key, this is going to exit. And that's all we really wanted to cover in this video. In the next video, we're going to build on this a little bit and do some processing of the video frame from the camera and then send the post-processed output to the display. So that's going to be a little bit more interesting to take a look at. So that's it for now, and we'll see you next time. In this section, we're going to describe for you how you can save videos to disk. In a previous video, we described how you can send the streaming output from your webcam to the output display, but here we wanted to cover how you can actually write that to disk. So we're going to start by specifying a source here. This could have been the webcam, but here in this example, we're going to specify a file from disk and read it in by creating a video capture object here. And so here we're specifying as the input argument to this the source for the video file. So this is our video capture object here. And in this next section, we're just going to simply check that that was successful. And then scrolling down here a little bit, we're going to use the read method from that class to retrieve the first frame of the video and then use IM show to display that in the browser. So that's the first frame of the video. And we can actually load the video here in the browser as well with this command here. And we've already executed that. So I'll go ahead and play it just so you can see it. It's just a very short clip of a race car. Okay, so then down here, we're going to talk a little bit about the video writer function in OpenCV. So this function allows you to create a video file on disk, and it takes as argument the file name, and then this 4cc argument, and that stands for 4-character code that describes the codec that's used to compress the video frames. And then there's also the frames per second, and then the frame size. Now the frame size is important because that needs to be the dimensions of the frames that you have in memory that you want to write to disk. So we'll see an example of that below. So let's take a look at this next code section here. The very first thing we're going to do is use the video capture object to call this get method, which is going to retrieve for us the dimensions of the video frame that we have in memory. And then now we're going to create two video writer objects, one for an AVI format and one for an MP4 format. So you can see here in both cases we're specifying the file name and then the 4cc codec. And to do that, we're going to use this video writer underscore 4cc function here. And for an AVI file, you need to specify these specific arguments. And for an MP4 file, you need to specify it just like this. So you can take a look at the documentation and read up on this, but this is sort of the tricky thing associated with writing video files, getting this codec right, and then also making sure that the frame dimensions match the frame size that you're trying to write to disk. So let's now take a look at how we actually do this. We're going to create a while loop here, and we're going to use the read method from this video capture object to read every frame from the video file. And then we're simply going to pass that frame back out to those video writer objects that we just created up above, one for the AVI format and one for the MP4 format. And then when that's done processing, we're simply going to release the resources down here. So that's all there is to it, but we did want to point out that getting these codecs correct and making sure that the frame dimensions match the frame dimensions of the video frames that you have in memory are the two key things that you need to watch out for. So that's all we wanted to cover in this section, and thanks so much, and we'll see you next time. In this video, we'll be demonstrating some of the more common image processing techniques that are often used in computer vision pipelines. And to do this, we're going to build on the camera demonstration from the last video where we sent streaming video from the camera to an output window in the display. However, this time we'll be doing some image processing on the video frames first and then send those results to the output display. So we hope you find this informative, and to get started, we'll first take a look at the code and then execute it so we can talk more in depth about the various processing techniques and their associated parameter settings. So starting on line 39, we're defining the 4 different run modes for the script, which include a preview mode, a blurring filter, a corner feature detector, and a canny edge detector. Then on line 44, we're defining a small dictionary of parameter settings for the corner feature detector, and those include the maximum number of corners that the algorithm will return. Quality level is a parameter for characterizing the minimum acceptable quality of image corners. And the way that works is that the corner feature with the highest value in the entire image is multiplied by this parameter, and then that value is used as a minimum threshold for filtering corner features from the final list that's returned by the algorithm. So for example, if you had several features that were detected and the maximum value of those features was 100, then we'd multiply 100 by 0.2, which would be 20, and then 20 would be the threshold for determining whether or not a feature corner was detected. And then the next parameter here, the minimum distance, this is the minimum distance between adjacent feature corners, and this is measured in pixel space. So it's the Euclidean distance in pixel space, which describes how close 2 corner features can be in the list that's returned from the algorithm. And then finally, block size is the size of the pixel neighborhood that is used in the algorithm for computing the feature corners. So this next block of code starting on line 48 is very similar to the code in the previous video, where we're setting the device index for the camera, creating an output window for the streamed results, and then creating a video capture object so that we can process the video stream in the loop below. So here on line 61, we enter a while loop, and first line in that loop is to read a frame from the video stream. And then on line 66, I'm going to flip that frame horizontally, mainly as a convenience for myself so that it's easier for me to point things out in the video stream. And then here on line 68, depending on the run configuration for the script, we'll be executing one of these functions in OpenCV. Of course, if we're in preview mode, we're simply going to take the frame and set that to the result and then display that directly to the output window using IMShow. But for these other run modes, we're going to do some processing first and then send the processed results to the output window. So starting on line 71, here we're calling the canny edge detection function in OpenCV. And the first argument there is the image frame, and then there's 2 additional arguments, a lower threshold and an upper threshold. The upper threshold is used for deciding whether or not a series of pixels should be considered as an edge. So if the intensity gradient of those pixels exceeds the upper threshold, then we'll declare those pixels as constituting a sure edge. And likewise, for pixels whose intensity gradients are below the lower threshold, then those segments will be completely discarded. However, for the pixels whose gradients fall in between these 2 thresholds, we'll consider those as candidate edges if they can be associated with a nearby segment that has already been declared as an edge. So in other words, we're allowing for weaker edges to be connected to stronger ones if the weaker edges are likely to be along the same true edge. And we'll see an example of that when we run the demo for edge detection in just a little bit. Then the next function here is a blur function in OpenCV. And this blur function uses a box filter to blur the image. So the first input to this function is the image frame itself. And then this second input are the dimensions for the box kernel. So this would be a 13 by 13 box kernel that would be convolved with the image to result in a blurred image. So if the size of the kernel is smaller, then the blurring is less, and if the size of the kernel is larger, then you get more substantial blurring. And then finally, for the corner feature detector, converting the image frame to a grayscale image. And then on line 77, we're going to call the function good features to track. And although it isn't indicated in the name of this function, what this function does is compute corner features. So the first argument is a grayscale image of the video frame. And then the second argument is that dictionary of feature parameters that we described up above. And so what that returns is a list of corners that were detected in the image. And if we have one or more corners detected, then we're going to simply annotate the result with small green circles to indicate the locations of those features. And then after we're done with all this, whatever result we have under whatever run mode we've been working with, we're going to send that to the output stream. So this next block of code here is simply monitoring the keyboard for user input. The script was written so that the run modes could be toggled interactively. So for example, if you were running in preview mode and you wanted to transition to candy detection mode, you would simply type a C on the keyboard. So that's all there is. There really isn't very much code required to implement this. And at this point, we're ready to go ahead and execute the script, and we'll cycle through the different run options and talk a little bit about the results that we see. So this is the preview mode, and here we're simply sending the video stream from the camera to the output window in the display. So what I'd like to do next is toggle through the other filters that we implemented, and we'll start with the blurring filter. So I'm going to type a B on the keyboard, and you can see that the image has been slightly blurred. There's a few reasons you might want to do this. For example, if you had a noisy image, you could apply a small amount of blurring and still obtain an aesthetically pleasing result. But more importantly, in computer vision and image processing, we often use blurring as a pre-processing step to performing feature extraction. And the reason for that is that most feature extraction algorithms use some kind of numerical gradient computation, and performing numerical gradients on raw pixel data can be a rather noisy and not well-behaved process. So smoothing the image prior to performing gradients turns out to be much more robust and well-behaved. And so that's one of the primary reasons we use blurring in computer vision. So now let's take a look at the next option, which is the corner feature detector. So now I've turned that mode on, and you can see a small amount of corner features in the image. There's some here on the microphone. There's a few around my face here, and in particular there's several there in the painting of the horses behind me. And we're going to talk a little bit about how these features are generated based on the input arguments that we selected. And there were two input arguments that we talked about in particular. One was a minimum distance between features, which is fairly straightforward, and the other one was a quality level of the features. So first we'll talk about the minimum distance. So here I've got a textbook with some very well-defined characters on the front that have nice sharp edges, and we're detecting all kinds of corners in those characters. You can see that each of those letters probably has 2, maybe 3 corner features for each character. But when I move the book much closer to the camera, you'll see now that there are several more corner features associated with each character, and the reason for that is that those letters are much larger in pixel space. So now I'm not constrained by the minimum distance between the features because I've made the letters so much larger in pixel space. And then one other thing I'd like to talk about is drawing your attention to this section of the book here with this graphic image on it. If I put this very close to the camera, we're going to see that we detect all kinds of corners associated with the dots in that pattern of the book there. So the reason those are jumping around so much is that I'm having a hard time holding the book really still. But the main point is that I'm getting all these detections here. Now watch what happens when I lower the book and expose the text from the title of the book. As soon as I expose the text from the title, all the features associated with the graphic image below have been filtered out. So let's take a look at that again. I raise the book and I get all these features here. And now when I lower the book and expose the title of the book, all those have been filtered out. And the reason for that is that that quality level threshold we talked about is based on the highest score for a corner feature in the entire image. And because the corner features associated with these characters in the title of the book are so much stronger, their feature score is higher, and therefore we're effectively raising the detection threshold for corner features. So I just thought that was an interesting example of how that parameter is actually used and how it can affect the algorithm in your particular application. So finally, let's go ahead and cycle to the canny edge detection. So I'll toggle to that mode, and so now you can see the results of edge detection here. You can see the microphone is very well defined. The corner of my shoulder against the light background of the wall is very well defined. And then up here behind my shoulder, you see a painting of some horses, and the subject matter in that painting is partially defined, but there's a lot of broken edges in that painting. And so I thought it'd be interesting to talk about the threshold inputs for the canny edge detector and see if we can improve what that looks like. So before we do that, I'm going to make a screen snap of this video feed just so we can have something to compare to. So I'll put this aside, and now I'm going to edit the threshold for the canny edge detector. So previously the lower threshold was very close to the upper threshold, so there wasn't much opportunity for us to find some weaker edges and connect them to stronger edges. But if I lower this to something like 80, we now have an opportunity to consider weaker edges that might be associated with the stronger edges. So I'm going to go ahead and run this, and now we'll put these side by side for a comparison. So if you take a look at the image down below, you can see that, again, the outline of the horses was rather broken in some places. And now if you compare that to the video stream up above, you can see that there's been some improvement. We're effectively extending the definition of these edges because we're allowing those edges to be connected to weaker edges that were in between those two thresholds rather than discarding those edges altogether. So I thought that was an interesting way to demonstrate how those inputs affect the results. Obviously, all these algorithms require some experimenting and tuning, and things that will depend on your particular application. But we hope this was a nice introduction for you, and definitely encourage you to take a look at the OpenCV documentation on these functions and other functions, and write similar scripts like this one here and do some experimentation. So that's all we wanted to cover in this section, and we'll see you next time. In this video, we're going to be talking about image alignment, which is also referred to as image registration. Image alignment is used in many applications, such as building panoramic images from multiple photos, or constructing HDR photos from multiple images taken at different exposures. It's also used in the medical field for comparing digital scans to highlight small changes between images. So in this particular example, we're going to introduce the topic by showing how we can perform document alignment. The image on the left here is an image of a form that's been printed out and filled out by hand and placed on a table. And the goal here is to transform that image to an image on the right that would align with the original template of the form, and therefore make optical character recognition of this form a much easier task. So that's a preview of what we're going to talk about. So first, let's scroll down here a little bit and talk about some of the theory of transformations. So on the left here, we have an original image in the shape of a square. And one of the simplest transformations we can make is a translation, which is simply a shifting of the pixel coordinates in the original image to the translated image, as shown here. And then beyond that, we have Euclidean transformations, which now include rotation. But notice that the size and shape of the original image has been preserved. And then further to the right, we have affine transformations, which encompass Euclidean transformations, but also include shear and scale changes. So now we have some distortion, but notice that parallel lines remain parallel. And finally, we have the homography, which is the most general transformation for 2D images, which allows us to transform the original square into an arbitrary quadrilateral. And the reason this is useful and interesting is that it allows us to warp an image to effectively change its perspective. So just as a more concrete example, let's scroll down to this next section where we show two images of the same book taken from different perspectives. Here we're interested in talking about the homography between these two images, and specifically for the 2D plane, and each image is represented by the front cover of the book. So if we can identify at least 4 points in both images that correspond to the same physical location on the front cover of the book, then we can compute the homography that relates these two images. So for example, we've identified 4 different points in both images that we've color-coded that represent the same points on the physical book, and therefore we call these points corresponding points since they correspond to the same physical location, but are obviously represented by a different set of pixel coordinates in each image. So given we have a set of points like these, we could simply call an OpenCV function to compute the homography and then apply the homography as a transformation to the image on the left, for example, to effectively change its perspective to look like the image on the right. Just keep in mind that 4 points is a minimum required, and in practice we would want to find many more corresponding points. But thankfully there are other functions in OpenCV that enable us to do just that. So we'll take a look at those details further below in this notebook. And just getting back to the document alignment example, let's start taking a look at the actual code. So here on lines 2 through 3, we're just importing some required modules. And then the very next thing we're going to do is simply read in the images of the template form and also the scanned form. So we have those available to us. And in this next section here, we're simply displaying both of those images. So we've got the original form here on the left, and then the photo of the form that we've filled out on the table and taken a photograph of. And again, our goal is to take this image and apply homography to it so that it lines up with this form here on the left. So let's see how to do that. The very first step in this process is finding some number of key points in both images. And there's not a lot of code here, but there's a lot going on that needs some explanation. So lines 2 and 3 here are simply converting the images that we read into grayscale. And the reason for that is that the code that follows that is performing some feature extraction on these images only requires a grayscale representation of the image. And then there's this code right here that is configuring an orb object from this orb create class. So if you're not familiar with image features and feature extraction in computer vision, just know that various algorithms have been invented over the years to extract what we call features from images. And the objective there is to try to extract meaningful information that is contextually related to the image itself. So typically we're looking for edges and corners and texture in images, and people have tried to invent various ways to compactly represent that information. So orb features are one way to do that, and they're available in OpenCV. So here we're going to create this orb object, and then we're going to use that object to detect and compute key points and descriptors for each of the images. So let's just go over this. Each of these function calls returns a list of key points and a list of associated descriptors. So the key points are interesting features in each image that are usually associated with some sharp edge or corner, and they're described by a set of pixel coordinates that describe the location of the key point, the size of the key point, in other words, the scale of the key point, and then also the orientation of the key point. And then there's an associated list of descriptors for each key point, and each descriptor is actually a vector of some information that describes the region around the key point, which effectively acts as a signature for that key point. So it's a vector representation of the pixel information around the key point. And the idea here is that if we're looking for the same key point in both images, we can try to use the descriptors to match them up. So let's scroll down here a bit further and just talk about these two displays. So we've computed the key points and descriptors for each image, and here in these figures we're displaying just the key points. So the key points are the where all these red circles are key points. The center of the circle is the location of the key point. The size of the circle represents the scale of the key point, and then the line connecting the center of the circle to the outside of the circle represents the orientation of the key point. So those details aren't terribly important for this demonstration. I just wanted to point out that all these red circles represent the key points, but associated with each of these key points is a vector representation of the image patch at that key point, which we're not displaying. But it's the descriptors that are actually used to match up these key points. So notice that on the figure on the left, there's all these red circles here on the form. And on the figure to the right, there's a lot of red circles in regions on the form that aren't even located here on the left. So the list of key points for figure 1 and the list of key points for figure 2 are they're overlapping, but certainly there's probably some key points in both images that maybe are the same, and those are the ones that we're going to try to find, so that we can compute the homography between these two image representations. So so that's the introduction to key points. And now let's scroll down here a bit further and talk about how we match those key points. So the first step in this matching process is to create a matcher object by calling this descriptor matcher underscore create function. And we pass to that function some configurations that indicate the type of matching algorithm we're going to use, which is brute force, and then also the metric for computing the distance between the descriptors, which is a Hamming metric, a distance measure. And that's because the descriptors for orb are binary strings, so we therefore require a Hamming metric for that purpose. And then, so we use that matcher object to call the match function, which then attempts to provide a list of the best matches associated with those list of descriptors. And so now we get a data structure back here that contains the list of matches from the key points that we determined up above. And then once we get that list, we're going to sort the list based on the distance between the various descriptors. And then on lines 9 and 10 here, we're going to further limit that to the top 10% of the matches returned by the matching function here. And we're going to use that now to draw the matches in this code below, shown here in the image. So we're calling this draw matches function, and we're going to pass in the key points for image 1 as well as the image, and the same for image 2. As well as this filtered list of matches computed above. And if you take a look at these two images, you can see that several key points in this image match the key points in this image. For example, in the form over here, there's a little image of a person, and further down here it looks like an image of a house. And you can see that there were several key points in both images that were in that local region, and then this matching function determined that yes, there were several here on this form that matched this form. In other words, the descriptors matched close enough for us to call that a match. And so now we have a set of corresponding key points, right? But notice here, for example, right down here, this lavender line is going up to some other location on the form to the right. So that's not a match, but it turned out that the descriptor for the key point here and the descriptor for the key point here were very close, coincidentally, and so it decided that that was a match. It's okay to have some false positives here. The important thing is that we have an overwhelming number of actual matches, which will allow us to compute a homography. So then the final couple of steps here in the notebook are to first compute the homography. So to do that, we simply call this find homography function here and pass it both sets of key points that have been filtered by the matching process above. And then there's an optional argument here, which is the algorithm that's going to be used to compute the homography. And here we're indicating the ransack algorithm, which is definitely the one you want to use. It's very robust to filtering out outliers left over from the matching process computed above. And there's a little bit of code up here that requires us to change the format of the points so that to comply with the this find homography function. But that's a detail. The point here is that we can compute the homography from a set of corresponding key points. And then finally, once we have the homography, H, which is a 3x3 matrix, we can call this function warp perspective on image 2. And recall image 2 was the image of the filled out form sitting there on the table, and pass in the homography. And what we get back is the registered or aligned image as shown below here to the right. So now we've effectively changed the perspective of that image on the table, and it's very closely aligned to the image on the form here. And now this is obviously a much simpler task to process, automatically process this form on the right. This form on the right can be compared to the form on the left, and an algorithm could be written to, it knows where the last name field is on the form, so then it can easily recognize these characters here as the last name of the person that has filled out the form. So that's one example of how you can use image alignment or image registration, and there's many other applications as we mentioned earlier. So you can see in very few lines of code you can get this up and running. You can experiment with your own images, and it's a lot of fun to do so, and we encourage you to explore that more. So we hope this was helpful to you, and we'll see you next time. In this video, we're going to be describing how you can create panoramas from multiple images using OpenCV. Much of the processing pipeline used for creating panoramas is very similar to the steps we described in the image alignment video. Since panoramas require image alignment, we still need to find key points and descriptors in each of the images and also determine their pairwise correspondences through a feature matching process. And we also need to estimate the homographies to facilitate image warping. And then once images have been transformed in this way, we need an additional step to stitch and blend the images together so they look realistic. And fortunately, there's a high-level convenience function in OpenCV that's available in the Stitcher class that allows us to create panoramas by simply passing in a list of images. However, we do think it's important to understand the underlying concepts, but since we covered much of this material in great detail in the image alignment video, we're simply going to use the Stitcher class in this example to show you just how easy it is to create panoramas with a single function call. Just remember that images used to create panoramas need to be taken from the same vantage point, ideally on a tripod that is panning around the optical axis of the camera. And it's also important to take the photos at roughly the same time in order to minimize any lighting changes between the images. So adhering to these suggestions will lead to the best results. So let's get started and take a look at the code that's required. Here in this first cell block, we're importing some required modules. And then in this next code section, we're using glob to retrieve the file names from a subdirectory. And then in this for loop here, we're simply reading in each of the file names and converting the images from BGR to RGB, and then appending each image to a list of images. And then in this next section here, we're simply plotting each of the images so you can see the sequence here. There's 6 images total. And then finally, in the last section here, you can see that we're going to be able to create the panorama in just 2 lines of code. So we do that by creating a Stitcher object from the Stitcher_create class. And then we use that object to call the stitch method, and we simply pass in a list of images. And the result we get here is the panorama image. So that's shown below. The only thing we would mention at this point is that the return panorama includes these black regions here, which are a result of the warping that was required to stitch the images together. And we'd just like to mention that maybe one thing you might consider doing is writing your own code to programmatically crop out that black image. You could use a combination of thresholding techniques, bitmaps, and contour finding to do that task. So that's all we really wanted to cover in this section, and thanks so much, and we'll see you next time. Hi everyone, in this video we're going to be talking about high dynamic range imaging, also referred to as HDR imaging. And I think the best way to get started with this is to just take a look at the simple example below. Here we have 2 photos of a young boy. This photo below on the left was taken with an iPhone in standard camera mode. And in that case, the metering system on the camera attempts to determine what the main subject matter of the photo is, in this case the young boy, and then it tries to set the exposure accordingly. So it's done a nice job here. The boy is properly exposed. Yet the background, the sky and the clouds are completely washed out. And then sometimes the opposite occurs. Sometimes you'll get a background that's properly exposed, yet the foreground is just far too dark. And the reason this occurs is because the actual intensities in the real world scene far exceed the capability of the camera to record those values. Since most cameras only have an 8-bit per channel capability, there just aren't enough bits to capture the full dynamic range of the scene. So in contrast to that, we have the image to the right. This image was also taken with an iPhone in HDR mode. And in this case, both the foreground and the background are all properly exposed, and the photo looks fantastic. So how exactly is this done? Well, what the iPhone does is it takes 3 photographs at different exposures, and it takes them in quick succession so that there's no movement or almost no movement in between the 3 shots. And then it takes those 3 what we call low dynamic range photos and merges them to come up with a HDR photo like the one shown here. So that's the basic idea, and we'll talk about this in a little more detail down here below with a different example. So this is a common photo sequence of the old courthouse in St. Louis that's used to describe HDR imaging. You can see that there's 4 different images here taken at different exposures. The image to the far left underexposed quite a bit, although that there is some area here in the lower portion of the building that looks properly exposed and might contain some useful detail. And then further to the right here, there's a little bit more of the building that's properly exposed. Still, the center is nice too, and then these other areas here might provide useful information. And then even further to the right here, now the buildings in the background start to have proper exposure. And then finally to the right, the well-lit portion here in the center is completely blown out, but perhaps the background buildings and even the sky, for example, and then some of these areas in the foreground might contain useful information. So the hope is that collectively this sequence of 4 images across all pixels in the image will contain some useful information that can be merged together to form a single HDR image with proper exposure for all of the pixels. So let's take a look at some of the code that implements this example. Down here we're just importing some required modules, and then right here we're defining a convenience function that's going to read the images and the exposure times for each image. So in here we're just listing the file names of the 4 images, and right down here we're setting the exposure times for each of those images. We know what that is for this example, but you could also extract that information from the metadata in each image and do that programmatically. And then finally down here in this for loop, we're just reading each of the images in and converting them to RGB, and then returning the list of images and the exposure times. So the next step in the process, once we've read in the images, is to make sure they're properly aligned. And even though these images may have been taken in quick succession or even on a tripod in quick succession, it's important that they be very accurately aligned down to the pixel level or even the subpixel level. So just as an example, the image here to the left is an HDR image that was produced without alignment, and you can see that the zoomed in section here at the top of the building has several ghosting artifacts and just doesn't look quite right, and is not a true representation of that portion of the image. Now contrast that with the HDR image produced on the right. This was produced with alignment, and you can see that the top portion of the building looks much more correct. However, since the images that are used in this sequence are taken at different exposures, they actually look different, and therefore standard alignment techniques just don't work. However, there is a special class in OpenCV that uses bitmaps for this purpose, and that class is called Create Align MTB for Median Threshold Bitmap. So down here we're going to create an Align MTB object, and then use that object to call the process method from that class, and pass out the list of images, and then get back the list of aligned images right here. So once we've done the alignment of the images, the next step in the process is to compute the camera response function. And the reason we need to do this is because most cameras we use are not linear, which means, for example, that if the radiance in a scene is doubled, the pixel intensities recorded by the camera will not necessarily double. And this presents a problem when we want to merge images taken at different exposures. So for example, suppose the response function was linear, then the intensities of the input images could be simply scaled by their exposure times, which would put them on the same radiance scale, and then we could simply compute an average intensity at every pixel location across those images to synthesize an HDR image. However, since the response function is not linear, we need to estimate it so that we can first linearize the images before combining them. However, since the response function for various cameras are considered proprietary information by the camera manufacturers, we need to actually use the images captured by the camera itself to estimate the response function. And this is actually a rather involved optimization problem, but fortunately OpenCV has 2 different classes that we can use for this purpose, both named after the people that invented the algorithms. So let's take a look at the code in OpenCV that accomplishes this. The one we're going to be focusing on is create calibrate debevic. There's another one by Robertson. In either case, there's a class for each algorithm, and here we're creating a calibrate debevic object, and then we're using that object to call the process method for that class, and we pass in the list of images and the associated exposure times for those images, and we get back the inverse camera response function here. And so this next block of code here is simply plotting the camera response function. And you can see at the lower intensity values, the function is quite linear in this region here, and then starts to become nonlinear right about here. And then finally at the higher end of the spectrum, we start to see some clipping at 255 as the intensities in the actual scene exceed the recording limits of the camera. Also notice that the 3 channels are calibrated separately since the sensitivities are slightly different between them. And so now we can use this function to linearize the input images by mapping the measured pixel intensity in those images to the calibrated intensity so that the images can then be merged appropriately. So in this next section here, we use a separate class for that purpose. Here we're calling the create merge debevec class to create an object, and then using that object to call the process method in that class, pass in it the list of images, the exposure times for each of the images, and then the response function that we calculated up above. And that method then returns the HDR image that we've been looking for. So at this point, it's worth mentioning that the merging process intentionally ignores pixel values close to 0 or 255. And the reason for that is that pixel values close to those extremes contain no useful information. So it's common to apply a hat type weighting function to each of the input images to filter out those pixels from the merging process. So just to briefly summarize, because there are multiple images of the scene at different exposure settings, the hope is that for every pixel we have at least one image that contains an intensity that is neither too dark nor too bright. However, there is one problem that still remains, which is the intensity values are no longer in the 0 to 255 range. Of course, black is completely 0, but HDR images can record light intensities from 0 to essentially infinite brightness. So because they have a fixed range, they need to be stored as 32-bit floating point numbers. And since our displays require 8-bit images, we need one last step to bring the image intensities back down to the 0 to 255 range. So that brings us to the final step in the process, which is called tone mapping, which refers to the process of mapping HDR images to 8-bit per channel images. So there's several algorithms implemented in OpenCV for this purpose. Mostly designed to preserve as much detail as possible from the original image while converting it to 8 bits per channel. But the main thing to keep in mind is that there's no correct way to perform tone mapping. Sometimes the goal of tone mapping is to achieve an aesthetically pleasing image that isn't necessarily realistic. However, the algorithms implemented in OpenCV tend to be fairly realistic, yet they have some differences and also various parameters that are configurable for each of the algorithms. So in this first example, we're going to take a look at using Drago's method to create a tone map. And we start by calling the create tone map Drago class and to create an object, and then use that object to call the process method for that class. And we simply pass it the HDR image itself. And that returns the 8-bit per channel color image shown below here. It does a very nice job of properly exposing all regions of the scene there. It's very pleasing in my opinion, and even the background, the buildings there seem to be properly exposed. So a very nice result. And then moving on to the next example, this one is using Reinhardt's method, and it also looks very nice, perhaps not as aesthetically pleasing, but certainly very realistic and with everything properly exposed. And then finally, there's one more example down here that's almost a combination of the two, I'd say. A little bit of the glowing here in the center like the first image. And again, everything looking fairly realistic and properly exposed. So that's a summary of the HDR imaging process. We covered a lot of detail, but when you step back and look at how much code was required, it wasn't very much. So that's all we really wanted to cover in this section, and we'll see you next time. Thank you. In this video, we're going to be talking about object tracking. This is a really interesting topic and a lot of fun to experiment with, and we hope you enjoy this demonstration. So first of all, what is tracking? Tracking usually refers to estimating the location of an object and predicting its location at some future point in time. And in the context of computer vision, that usually amounts to detecting an object of interest in a video frame and then predicting the location of that object in subsequent video frames. And we accomplish this by developing both a motion model and an appearance model. The motion model, for example, will estimate the position and velocity of a particular object and then use that information to predict its location in future video frames. And then we can also use an appearance model, which encodes what the object looks like, and then search the region around the predicted location from the motion model to then fine-tune the location of the object. So the motion model is an approximation to where the object might be located in a future video frame, and then the appearance model is used to fine-tune that estimate. All of the code that we'll be using below is from the OpenCV API tracker class, so we'll talk about that a little bit more as we scroll down through the notebook here. So as a concrete example, suppose we're interested in tracking a specific object like the race car identified here in the first frame of a video clip. In order to initiate the tracking algorithm, we need to specify the initial location of the object. And to do this, we define a bounding box shown here in blue, which consists of two sets of pixel coordinates, which define the upper left and lower right corners of the bounding box. And then once the tracking algorithm is initialized with this information, the goal is to then track the object in subsequent video frames by producing a bounding box in each new video frame. So we'll talk more about this below, but before we get started with the code description, let's just take a look at the tracking algorithms available in OpenCV. There's 8 different algorithms listed here, and we're not going to review the details of each of these, but it's worth noting that depending on your application, one might be more suitable than the other. For example, some are more accurate, some are faster, some are more robust to occlusions of the object being tracked. So that's worth keeping in mind when you experiment with all of these different algorithms. And then one other thing that's worth mentioning is that the GoTurn model here is the only one that's deep learning based. And we'll talk a little bit more about that further below. So just as a preview to get started here, I've got the test video clip right here, and let's just play it 1 or 2 times. So you'll notice that early on the car's appearance is relatively constant as well as its uniform motion. But as it starts to make a turn here, you'll see that we see the broadside portion of the car, and then the lighting is starting to change quite a bit, and then now it's getting smaller and smaller off into the distance. So those types of things are going to represent some challenges for some of the tracking algorithms. So we'll talk a little bit more about that. So let's start taking a look at the first code block in this notebook. Here we're just importing some modules that are required. And then on line 10, we're indicating the file name for the video clip that we're going to process. And then here we're defining some convenience functions that will allow us to render bounding box information on the output video stream, as well as annotate the output video frames with some text. And then recall earlier we described that one of the algorithms is the GoTurn model, which requires an inference model. So this block of code here is required to download that inference model. And then this figure here is a very high-level description of how the GoTurn tracker is trained and used. So in the center here, we're indicating that we have a pre-trained neural network model, also known as an inference model. And it takes as input 2 cropped images, one from the previous frame and one from the current frame. It uses the bounding box from the previous frame to crop both of these images, and therefore the object of interest is located in the center of this previous frame. And obviously if the object has moved in the current frame, then it won't be centered in this cropped image, because we're using the bounding box from the previous frame to crop both of these images. And then it's the job of the inference model to then predict what the bounding box is in the output frame here. So that's just a high-level description of how that works. So let's scroll down a bit further here and take a look at this next code block. This is where we're going to create a tracker instance. And we start by defining a list of tracker types here, where we're just indicating the list of string names that are available in the OpenCV API. And then depending on the tracker algorithm that you wanted to execute, you would just set the appropriate index here into that list. And since that's specified as 2, then we'd be indicating that we'd like to execute the KCF tracker in that list. And this if-else block here would then call the appropriate class to create the tracker object. So in the case of the default, we'd be calling the tracker KCF _create class to create a tracker object of that class. So let's scroll down here to the next section. In this block of code, we're setting up the input-output video streams. So here on line 2, we're passing in the video input file name and creating a video input object. And then on the next line, we'll go ahead and read the first frame from that video file. And then down here on lines 13 and 14, we're doing a similar thing for the output video stream and creating a video out object, which will then write results to from our tracking algorithms. Now in this section here, as we talked about earlier, we need to define a bounding box around the object that we're interested in tracking. And we're accomplishing that here just manually. Notice that I'm specifying the 2 sets of pixel coordinates here for the upper left and lower right corners of that bounding box. But in practice, you would either select that with a user interface or perhaps use the detection algorithm to detect objects of interest for tracking and do that programmatically. But for demonstration purposes here, we're just going to set that box manually. And then down here, we're now ready to initialize the tracker. So in order to do that, we use the tracker object here and call the init function, and we pass it the first frame of the video clip and then the bounding box that we defined manually up above. Okay, and then once that's defined, we're ready to enter a loop here to process all the frames in the video. So this first line of code in the loop on line 2 is reading the next frame from the video clip. And then on line 10 here, we're going to pass that frame to the tracker update function and hopefully return a bounding box for the object that was detected. So if we detect the object and we retrieve a bounding box from the update function, then we'll go ahead and render a bounding box rectangle on the current frame. And if we didn't detect the bounding box, then this OK flag would be false, and we'd simply annotate the frame with a tracking failure message indicated here. And then further below, we'll also annotate the video frame with the type of tracker that's being used and the frames per second that's been calculated, and then write that frame out to the output video stream. So that's all this loop does. It cycles through each frame in the video clip and calls the tracker update function and then annotates the frames and sends them to the output video stream. So let's scroll down here a bit further and take a look at some results. So this notebook has already been executed a few times for different trackers, and so we're just going to replay those results. So all of these results shown here are the output video streams that have been annotated with tracker results. And you can see in this first example, this is the KFC tracker, and I'm going to go ahead and play this, and we'll take a look at how it performs. So it looks like it's doing a fairly good job of tracking the car. A little bit off center, but still maintaining track on what's obviously the car in the video frame. And then as the car rounds the corner, it's doing okay. And then shortly here, we're going to see that it has a little bit of difficulty right here at the end. It drops track on the car. So let's take a look at the next example. The next example here is the CSRT tracker, and we'll go ahead and take a look at that. So this one does a little better job tracking the car with the bounding box encompassing most of the car and centered on the car, pretty much. And then as the car makes the turn here, the box is on the front of the car, but it's still got the car in track, I'd say. And then right there at the end, it looks like it's having difficulty maintaining a precise location for the car. So let's go down to the final example, and this is the Go Turn tracker. Again, trained on a deep neural network offline. So let's take a look at this. So it looks like it's maintaining track as well. The bounding box is a little narrower, but centroided on the car. And then as it rounds the corner here, it still maintains track. The car is pretty much in the center of that bounding box for the most part. It gets a little wider there, but then as it tails off, it maintains track on the car right there at the end. So out of the 3 examples, the Go Turn tracker probably did the best job of maintaining track throughout the entire video stream, and especially right there at the end, still able to keep the car essentially in the centroid of that bounding box. So we hope that gives you a good feel for how to exercise the various tracking algorithms in OpenCV, and especially the small amount of code that's required in order to get something up and running. So we encourage you to experiment further, try some of your own videos, and experiment with the various algorithms. And we hope this was helpful to you, and we'll see you next time. In this section, we're going to show you how you can use a pre-trained neural network to perform face detection. And to do that, we're going to be using the OpenCV framework that will allow us to read in a pre-trained model and perform inference using that model. So to get started, there's a little bit of code here at the top of the script that sets the device index for the camera, creates a video capture object, and then creates an output window for sending all the results to the display. However, since we've covered this in a prior video, we're going to skip that discussion and focus our attention here on line 47. So OpenCV has several convenience functions that allow us to read in pre-trained models that were trained using various frameworks. So for example, Caffe, TensorFlow, DarkNet, and PyTorch are all deep learning frameworks that allow you to design and train neural networks. And thankfully, OpenCV has built-in functionality to use pre-trained networks to perform inference. So just to be clear, you cannot use OpenCV to train a neural network, but you can use it to perform inference on a pre-trained network. And that's very nice for getting familiar with using neural networks and getting started. So this function, readNet from Caffe, is a function that's specifically designed to read in a Caffe model, and it takes two arguments. The first argument here is the prototext file, which contains the network architecture information. And then the next file is the Caffe model file, and that's a much larger file that contains the weights of the model that's been trained. So notice here that we're pointing to these files on our local system. However, they can also be downloaded from the internet. So let's take a look at the Git repo that contains these models. So here in this repo, there's several scripts at this level. And if you scroll down a bit, you'll see that there's a download models script right here. And if you scroll down a little bit further, you'll see that there's a README file here that contains a description and instructions on how to use that script to download various models. So it turns out that that script actually references a models.yaml file, which is right here, and it's instructive to go ahead and take a look at that. So at the top of that file, you'll see a block here that references the Caffe model that we're actually going to be using. Here is the URL to download the weights file, and then there's several other parameters here related to how that model was trained. And so we'll talk about these in a minute because we're going to reference these values in our script. But just notice that there's a mean value, a scale factor, a height and width, and also this RGB flag. So let's go back to the script and continue on. When we call this readNet from Caffe method, it returns for us an instance of the network, and we're going to use that object further below to perform inference on our test images from the video stream. So this next section here is identifying the model parameters that were associated with how the model was trained. And it's important that we're aware of these because any images that we pass through the model to perform inference on also need to be processed in the same way that the training images were processed. So here we have the size of the input images that were used to train the model, 300 by 300. And then here we have a list of mean values from each of the color channels across all the images that were used in training. And then this confidence threshold is a value that you can set that will determine the sensitivity of your detections. So then scrolling down here a bit further, we enter this while loop. And the first thing we do in the loop is read one frame at a time from the video feed. And on line 59, I'm going to flip that frame horizontally just as a convenience for myself so that when I point to things in the field of view of the camera, it's easier for me to do that. But it has no consequence other than that. And then on line 60 and 61, we're simply retrieving the size of the video frame. And then on line 64, this is important. Here we're doing some pre-processing on the image frame, calling this method blob from image. So there are several arguments here, and we'll go through these. But all this has to do with is doing some pre-processing on the input image and putting it in the proper format so that we can then perform inference on that image. So it takes as input the image frame from the video stream. This next argument is the scale factor, and recall that the scale factor in that YAML file was 1, but that's not always the case. When models are trained, sometimes the images are scaled to different ranges, and if that was the case, this would have been something other than 1. Then this is the input width and height of the images, so that was 300 by 300, and we've identified that up above. And then this is the mean value, which is going to be subtracted from all the images. And then there's this flag swap RB. RB stands for red blue. Notice that that's equal to false, and the reason for that is that both Caffe and OpenCV use the same convention for the 3 color channels, but some models use a different convention, and in those cases you'd have to swap the red and the blue channels. And then finally there's this last input argument, crop. This last argument indicates that you can either crop your input image to be the correct size, or you can resize it. So because crop is set to false, that means we're going to simply resize the image to be 300 by 300. And then this function call then returns a blob representation of the input image frame with all that pre-processing handled, and then there's also a format change. And then we pass that blob representation of the image to this function set input, and that prepares it for inference. And then this very next line, net.forward, makes a forward pass through the network and is performing inference on this representation of our input image. And then for some number of detections returned by the inference, we're going to loop over all those detections, and right here we're going to determine if the confidence for a particular detection exceeds the detection threshold. And if it does, we'll proceed further and query the detections list for the bounding box coordinates of that particular detection. And then the rest of the code here is going to render a bounding box rectangle for the detection on the image frame right here. And then we're also going to build a text string that indicates the confidence level for the detection, and annotate the image frame using OpenCV rectangle and put text functions right here. And then once we're done processing all the detections, we'll finally call this get performance profile function, which is going to return for us the time required to perform inference. And we're going to convert that to milliseconds, and then build another text string here and continue to annotate the frame with the amount of time that it took to perform the inference. And then finally, we're going to use IMShow to display that annotated frame to the output window. So that's all there is. There isn't much code required to perform inference on the model, and in fact, most of this code here is related to annotating the frame itself. So at this point, we're ready to go ahead and execute the script, and when we do that, we'll cycle through some demonstrations and see just how this performs. So here you can see the model is detecting my face very nicely, and I can obscure my face a little bit with my hand, and it still does a nice job of detecting my face. The reason I like using the video stream is that it's just a lot of fun to experiment with. You can hold up images to the camera and experiment with the scale and orientation of the images in real time. And so we're going to do that. I've got a magazine here that I found a lot of interesting images in, and so we'll cycle through that and we'll see what you think. So I'll scooch out of the way here and we'll get started in just a second. So in this first image here, you can see the boy's face is in a downward pose, and also his bangs are obscuring his forehead and even a portion of his eyes, yet the model still performs nicely in detecting his face. So we thought we'd start with this image and then progress to some that are a little bit more difficult. In this next image here, you can see the young girl's face is also in a downward pose, but is also a profile view. And then, of course, she's wearing eyeglasses, which may present an additional challenge. Yet the model still performs nicely. These next couple of images have a mixture of the face as well as some graphics mixed in. So kind of a mixed media obscuration of the face, if you will. And the model does very nicely on this one. And here's another example on the opposing page. And in this case, notice the different scales of the images that are being detected. But the model still is handling things very nicely. So this next one coming up is my favorite, primarily because it's the most impressive. So take a look at this. As you can see, the woman's face is heavily occluded, and there's even been some manipulation of the image in the area around her eyes and also around her chin and mouth, almost a blurring to some extent. So those both represent significant challenges, yet the model is able to detect her face fairly well. And we hope this gets you really excited about computer vision and especially deep neural networks. Just remember that you don't have to train your own models. You can use a pre-trained model like we've done here in this demonstration and write just a small amount of code to do your own testing with your own images. So that's all we wanted to cover, and we encourage you to do that, and we'll see you next time. In this section, we're going to describe how to perform deep learning-based object detection, and specifically we'll be using a neural network called single-shot multi-box detection trained using TensorFlow. And like previous videos, we're going to be using OpenCV to both read the model and perform inference on some sample test images. If you look at this name here, it says SSD, which stands for single shot multi-box detection. The single shot refers to the fact that we're going to make a single forward pass through the network to perform inference and yet detect multiple objects within an image. And like other types of networks, SSD models can be trained with different architectural backbones, which essentially means you can model a single concept yet use different backbones depending on your application. So in this case, we're using a MobileNet architecture, which is a smaller model intended for mobile devices. But before we get started, I wanted to point out this resource here. There's a TensorFlow object detection model zoo at this URL. And if you go to that repository, you can download a variety of different object detection models. So we just wanted you to be aware of that. In this particular case, we're going to be using the SSD MobileNet V2 Cocoa 2018 archive listed here. And if you extract that archive, you'll see it has a structure like the one shown here. And we simply wanted to point out that you only need one file from that archive, and that would be the frozen inference graph right here, which is the weights file for the model. And there's actually two other files that we'll need to have in order to run this notebook. So let's scroll down and take a look at those as well. So right here, we're specifying the three models that are required, the frozen inference graph, which we just described above. And then there's a configuration file for the network that's indicated here with the .pb text extension, and then also the class labels for the data set that was used to train this model, which is the Cocoa 2018 data set. You can actually Google that Cocoa data set and retrieve this class labels file from numerous places on the internet. But in terms of this configuration file, there's actually a script that you can use to generate this file from the frozen inference graph. And that script is indicated right here. We've already executed this notebook, and so we have all these files locally on our system, but we just wanted to review with you how to obtain each of these three files. And then one thing that's worth pointing out at this point is take a look at the class labels for this file that we printed out down here in the lower portion of the screen. Notice the difference between a deep learning object detector and a traditional computer vision object detector. We used to have a detector for every class. So for example, we had a face detector and a person detector and so on, and those were all separate models. But with deep learning models, we have enormous capacity to learn, so a single model can detect multiple objects over a wide range of aspect angles and scales, which is the real beauty of deep learning. So let's scroll down here a little bit further to the next section of the notebook. So summarized here are the three steps that need to be performed. First, loading both the model and the input image into memory, and then detecting objects using a forward pass through the network, and then finally displaying the detected objects with bounding boxes and class labels. And so the first step is indicated here, where we're calling the OpenCV function readNet from TensorFlow, and that takes as input a model file and the configuration file, both of which we specified above. And then that's going to return for us an instance of the network here, which we'll use further below to perform inference. Next, here we're defining a convenience function called detect objects, and it takes as input the network instance and then the test image. And then we've seen this before here. There's another OpenCV function called blob from image, and this takes as input the test image and then several other arguments that are related to pre-processing the test image. I recall that when we prepare an image for inference, we need to perform any pre-processing on that file that was performed on the training set. And so this function contains several arguments related to the required pre-processing. This first argument here is a scale factor, and it's set to 1, which indicates that the training set didn't have any special scaling performed on it. Then here we're indicating the size of the training images, and we're indicating that right here with the 300. So the test image will need to be reshaped according to this size. And then the next argument is this mean value. If the training images had had a mean subtracted value applied to them, then this would have been some other vector. But since those images don't require any mean subtraction, we're simply indicating zeros here. And this next argument here, swap RB, for whether or not we want to swap the red and the blue channels. And then in this case, we do want to do that since the training images used a different convention than what's used by OpenCV. And then finally, this crop flag is set to false, so that means that the images are simply going to be resized as opposed to cropping them to the right size. And then this function returns for us a blob representation of that image that's been pre-processed. So there's a pre-processing step, and then there's also a format conversion step, if you will. And then this blob representation of the image is passed to the set input method to prepare the image for inference. And then finally, we perform inference on the test image by calling the forward method, and that returns for us some number of objects that have been detected, and then we'll return that from this function. So there's a couple more convenience functions down here below, so let's take a look at those. This one here, display text, takes in the test image frame and then a text string and some coordinates. So this is a function that will simply annotate a bounding box with the class label by drawing a black rectangle here and then annotating the frame with some text indicating the class label inside the black rectangle. And then finally there's this display objects function, and then it also takes in the test image and then a list of objects that were detected and then the threshold for detection here. And here we're retrieving the shape of the input test image, and then we're going to loop over all the objects that were detected by the network and retrieve their class IDs and their scores. And in this next section here, we're further going to retrieve the coordinates for the bounding box of that object and convert those coordinates to the original test image coordinates. And then finally, if the score for this object is greater than our input threshold, then we'll go ahead and annotate the frame with the class label, calling that display text function we just described above. And then finally, we're going to render the test image frame with the bounding box rectangle in white right here. So let's take a look at some results. So you can see here we're reading in a test image, and now we're going to use the function we created above, detect objects, passing it the network instance here and the image we just read in here, and the return from that function is a list of objects that have been detected, and then we're going to call the display objects function, passing in the test image and the array of objects. And you can see the result down here. There's all kinds of objects being detected. There's a person here, there's a bicycle here, there's a car here, there's cars off in the distance, and even way out in the distance here you can see a traffic light's been detected. So this is a very robust object detection algorithm, has about 80 classes. And let's take a look at another example down here below. This is a sports scene. So you can see the same sequence here, reading in the image, calling detect objects, and then display objects. And in this case, we're getting both people in the image, the bat, the baseball glove, which is really nice, and then the baseball. But notice that the baseball actually has a false positive. There's only one baseball there, yet the detection algorithm is reporting 2, so there's a false positive there. But other than that, it's done a very nice job. And let's take a look at one more example. So here's another sports scene here, and you can see it's detecting the soccer player here, the soccer ball here, and then there's a false positive here. It thinks that the tip of his shoe is actually another sports ball. And one thing we can do in cases like this is after you've established some number of false positives, you can actually take these image examples and perform what's called hard negative mining by training the network with additional examples like this to reduce the number of false positives. So we hope that's a nice introduction for you to object detection, and that's all we wanted to cover in this section, and we'll see you next time. In this section, we're going to show you how you can perform 2D human pose estimation on your own images and video by using a pre-trained model called OpenPose. OpenPose was developed at the Carnegie Mellon Perceptual Computing Lab, and if you're not familiar with pose estimation, the figure below from the OpenPose research paper provides a nice graphic. So essentially the problem requires taking an input image that may contain one or more people and then identifying the key points associated with the major joints in the human anatomy and then logically connecting those key points as shown in the figure on the right-hand side here. The model actually produces two types of output, part confidence maps and part affinity maps. However, for the code demonstration below, we'll only be using a single person in the image, and therefore we'll only need to make use of the confidence maps, which are also referred to as probability maps. And we'll see how that's done further below. So just a brief history, for a long time human pose estimation was a very difficult problem to solve robustly, especially on some of the more challenging benchmark cases. The reason the problem can be hard is that joints are not always very visible. There are numerous opportunities for occlusions of one type or another, and then clothing or other objects can further obscure the image. And then there's the added complexity of not only identifying key points, but associating them with the right people if there's multiple people in the image. However, once deep learning was applied to this problem domain just a few years ago, we really began to see dramatic improvements, and it's been really exciting to see just how well these models now perform. So in this demo, we're going to be using the OpenPose Cafe model that was trained on the multi-purpose image dataset, and we'll be doing that using a single image, which we'll get to in just a minute, but we wanted to point out that human pose estimation is often applied to video streams for various applications, such as intelligent trainers, for example. So we wanted to just start with some example results on a video clip to whet your appetite, and then we'll walk through the code for a single image implementation. But just remember that the code can easily be adapted to process a video stream, as we've shown in prior videos. So just scrolling down here a little bit to this first example, this video clip which we're going to show was processed using OpenPose, and the OpenPose results have been overlaid on the video stream. So let's take a look. So all three hockey players are wearing bulky uniforms, which is a challenge, and then they're also occluding each other to some extent, yet the model is performing pretty nicely if you just take a look at the results. It's a lot of fun to work with, and of course we'll be taking a look at a single image example, but we thought it was instructive to show you how exciting that is to process videos. So let's continue on and take a look at the rest of the notebook. So in this first section here, we're simply specifying the model. Here is the prototext file here, and then the Cafe model or the weights file right here. We downloaded those already and have already executed this notebook, but there are references in this notebook here for where you can download these files. And then in this next section here, we're specifying the number of points in the model and the associated linkage pairs here by their indices. So these each of these blocks here refers to a linkage in the human anatomy, and 0 starts at the head, 1 is the neck, 2 is the right shoulder, 3 is the right elbow, and so forth. So this is a mapping that the model uses during training, and we're going to need this mapping to process the output from the network further below. And then right here on this line, we're calling the read net from Cafe. We've seen that before in a previous video, where we just pass in the prototext file and the weights file for the trained network. And that creates for us an instance of the network, and we'll use that below for inference. So now we're ready to read in our test image, and we're doing that right here in this code block with IAMRead, and then we're also swapping the red and blue color channels here on the next line. And then these two lines are retrieving the size of the image, which we'll use further below. So let's take a look at the image. This is a picture of Tiger Woods hitting a driver from the rear view at the top of his backswing. And the reason I chose this image is because it's a little bit challenging and makes a nice example. His upper body, notice, is at right angles to his lower body. So his lower body is facing to the right of the camera, and his upper body is actually facing the camera. And then his left arm is occluding his right shoulder. So that's going to make things a little more complicated. And let's continue on to the next section. So now we're at the point where we're ready to go ahead and pre-process our image. Recall that when networks are trained, they're trained with training images that have a specific size and potentially some scaling performed on them. And we need to make sure that whatever images we're using to perform inference on are pre-processed in the same way. So here we're setting the net input size of 368 by 368. And then we're calling the OpenCV function blob from image, and recall from our previous video that this takes several arguments related to all this pre-processing. And then it's also going to convert the image into a blob representation, which will pass into this set input function to prepare the network for inference. So let's review these arguments briefly. So this first argument is the image itself, and then the second argument is a scaling factor, which is the same scaling factor that was applied to the training images. So we need to perform that same transformation here on the input image. And then here we're just indicating the net input size, which we just talked about right here above, 368 by 368. There was no mean value subtracted from the training images, so we're simply indicating a vector of zeros here. And then the swap red-blue flag here is set to true. And we're not cropping, we're going to resize our input image to match the size of the images that were used during training, which was 368 by 368. So now we're ready to use the model to perform inference on our test image, and we do that right here by calling the forward method, and that returns for us the output from the network, which consists of both confidence maps and affinity fields. And as we mentioned earlier, we're only going to be using the confidence maps for performing the key point detection in this demonstration. And so for each point, we're going to receive a probability map, and then we're simply going to, in this next two lines of code, plot each of these probability maps. And you'll see that these are color-coded. They're heat maps indicating the probability of the location of the detected key point. And so red is a very high probability. So in each of these probability maps, you'll see this is the likely location for key point 0, key point 1, key point 2, and so forth. So remember, this one corresponds to the head, this corresponds to the neck, this corresponds to the right shoulder, and so forth. So we can use these probability maps to overlay those key points on the original image, and to do that, we're going to have to scale these in the same scale as the input image. And so that's what this next block of code is performing. So right here, we're using the output shape of the network, in other words, the shape of the probability maps, and also the input shape of the test image to compute two scale factors, x and y, that we'll end up using below to determine the location of the key points in the actual test image. But before we do that, we're going to need to determine the location of the key points in the probability maps. So that's what we're going to do in this next code block here. This for loop is looping over all the key points, and for each key point, we're going to retrieve the probability map from the output array from the network. And then we're going to call this OpenCV function min-max location and pass it the probability map. And this is going to return for us the location of the point associated with the maximum probability. And so the coordinates of the point are in this variable here, point. And then once we have that location in the probability map coordinates, we're going to multiply it by the x and y scale factors we computed above to get the key point location in the original test image. And then if the probability returned by this function is greater than some minimum threshold, which we set above, then we're going to go ahead and take that xy point now in the coordinates of the test image and then append it to a list of points. And so now we're ready to render those points on the test image. So let's scroll down here to our results. First, let's just take a look at the image. So this is the input image here with all the key points annotated on the frame. And then the image to the right is the same key points, but without the numbers, but with the linkages connected. So two different views of the same data, really. And if you take a look at this area that we knew was going to be difficult, in other words, the head was at 0, the neck was at 1, the right shoulder at 2, the right elbow at 3, the right wrist at 4, it looks really nice, even though the left arm is occluding the right shoulder. And I mean, if you go back over here to the image on the right, you can see the skeletal view, and that looks pretty spot on. So it did a nice job of detecting the key points and putting them together in a way that makes sense. But let's just go ahead and walk through this code a little bit. So up here on these first two lines, we're just making a copy of the input image, and one's going to be called points, and the other one's going to be called skeleton. And then we're going to loop over all the points that we just created in the for loop above, and those are the coordinates of the key points in the test image coordinate frame. And then we're going to use OpenCV circle and put text functions to draw and label those points on the IMPoints image, which was the image to the left down here. And then further, we're going to render the skeleton view that's displayed down here to the right with this for loop. So we're looping over all the pose pairs, which we defined further up in the notebook. And then we're retrieving those pairs, and we're going to set those to part A and part B here, and then use those as indices into the points list that we created up above, which contains the list of key point locations in the test image. And now we're simply going to use OpenCV line and circle functions to draw a line from one joint to the next and color code it, and then also draw a circle at the first key point in that link. So, and then here we're just using IMShow to display both these images below. So that's all there is to it. There wasn't much code in this notebook. Since we're leveraging the capability of OpenCV to perform inference for us, really the code amounts to a few function calls and then a little bit of a logic to parse the outputs and render the information on the original image. And just for fun, I went ahead and ran the same model on a photo of my son, who also plays golf. And this is a view of his follow-through. And the model does a pretty good job, but I'll have you notice one thing here is that the if you look over here to the right, the neck and the right shoulder are off a little bit for some reason. So this is the head, this is 0.0, this is 0.1, which should be right here, and this is the right shoulder, which should be over here. But notice his right shoulder is actually occluded quite a bit by his back, so it's almost not even visible. So it's definitely a challenging pose. And, you know, it was a lot of fun to try this out. So the main point, though, is that you can use a pre-trained model, leverage the inference capabilities of OpenCV, and start playing around with your own images and video. And we think you'll enjoy doing this. And thanks so much. And that's all we wanted to cover in this video. And we'll see you next time. Well, thanks, everybody. I hope you enjoyed the course that we just covered in the Getting Started series in computer vision. We covered a lot of ground and a lot of material at a pretty good level for a Getting Started series. And I think this is a good opportunity for us to talk with Dr. Satya Malik, who's the CEO of OpenCV.org, to get his take on how do you get a job in computer vision, for example, and some of the other course offerings that we offer on OpenCV.org.
Thanks a lot, Bill. It's a pleasure to talk to this audience because they have just completed their first steps in OpenCV, and I can understand, you know, it's very exciting. It's a very exciting field. And the next thing people ask is, how do you get a job in computer vision and AI? And the path is, you know, you have to dedicate yourself. You have to commit yourselves to learning various aspects of computer vision. But there is a path through which you commit to that path, you will find a job at the end of this path. And as you know, Bill, your own journey is one great example of that. You started your journey in aeronautics and astronautics. You did your master's from MIT in that area. And for the longest time, you were in that area. But then you made a switch because of in your job, you wanted to use AI. But then gradually you made a switch to computer vision and AI. I would in fact love to hear that. We can start with that little story.
Yeah, sure. I mean, I'm excited to talk about that. So I worked in the space and defense industry for many years. Very rewarding experience. I loved the idea of space travel when I was a young child, and ended up graduating with a degree in aeronautics and astronautics. And it was a wonderful experience for me. Along the way, I had the opportunity to work on a project that involved something completely unrelated to what I was doing. I was working, performing technical management on a project related to machine learning at the time. And this was about 8 or 9 years ago. And it was really exciting for me to see just how stunning the results were to some of these use cases that we were working on. It was a small research project, and Shortly after that project, I began a journey on expanding my continued education. I studied machine learning and also image processing. And as I moved forward with that, I really felt a strong passion for working in the field of computer vision. So I spent quite a bit of time taking extra classes while working full time, early morning study sessions, and lots of weekends spent learning all this material. And I'm happy to say that I've landed in a very nice place, and I'm working in the field full time now, and I really enjoy it. Thank you.
Yeah, so that's, and you took deep learning with PyTorch, which is one of our courses as well.
Right, right.
And so what I was saying is that there is a path. It's not necessarily easy, especially if you're working full time. You have to dedicate your nights and weekends, but there is definitely a path for people who are interested. And if you're a student, there is a very clear path, right? It's a relatively easy path. One thing I like to say, people, is that if you want to learn about physics, you have like 200 years of history in physics.
Right.
So you have to learn all that material to get started in physics, right? Before you can contribute in physics. But for computer vision, it's a relatively new field, right? Computer vision, you can say that even though research started in 1960s, it's really now that algorithms that work in the real world are available to the general public. So you're literally talking about a decade of worth of techniques, which is not a lot, frankly. So for people who are trying to start in this area, I would say that set aside, and especially people who are not doing it full time, they should set aside anywhere between 6 months to a year to learn the material, to get completely, and that's hard work, right? 6 months to a year of hard work, nights and weekends, to get their foothold in this field where you can think about making a career switch. There are other people in our courses who were able to make a switch by taking just one course, but I usually recommend that you need to understand traditional computer vision algorithms, and you also need to learn deep learning algorithms. So you need to have a flavor of both of those things. Let me actually start by explaining what are the various aspects of AI, so that we lay out the land, and then it will be easy for beginners to understand what are the various topics we are talking about. Now, the first question people ask is, what is artificial intelligence? So it's a very fuzzy term. It doesn't refer to a specific technique, but in general, whenever we try to make machines think like humans, we call it artificial intelligence. And there are various ways of solving this problem. You can think about a rule-based system where you're encoding all the rules. Like in a chess game, you could say that, oh, if you do this, I'm going to do this step, right? And that used to be very popular a few decades back, but then people realized that you can actually train the machine by giving it data, not explicitly telling it, what the rules are, but it will automatically figure out things based on data. So that's machine learning. Machine learning is a subset of AI techniques where we care about data. The other part is deep learning. You might have heard a lot about this new kind of technique called deep learning, which is nothing but solving machine learning problems using deep neural networks. And in our course, we tell you why it is called deep. It's a very subtle thing, why it is called deep neural networks. But it is basically solving AI problems using neural networks. So that's deep learning. Computer vision is actually, there is an overlap of computer vision, deep learning, etc. Computer vision basically means the analysis of images and videos. And it is different from image processing, because in image processing, you have an input image and the output is also an image. You could be encoding an image, you could be enhancing an image, etc. So that all is under image processing. In computer vision, usually we have an input image, and the output is information that we want. So the image could be this video session, but the output could be the faces that we detected, right? So it is image in and information out. Not only that, in computer vision, we also handle many things that have nothing to do with artificial intelligence. For example, in this course or in this video series, you learned how to create panoramas. That is a classical computer vision technique, and it has nothing to do with artificial intelligence because you're stitching images together, you're using the geometry of image formation, you're using all these techniques, which are not really machine learning or AI, right? But they are still very useful techniques. So there is an overlap between artificial intelligence and computer vision, but computer vision does a lot more other things also. For example, the whole field of 3D computer vision, there used to be very little AI in that. Now, even AI is being used to enhance those fields also. So that's the general lay of the land.
So from the artificial intelligence standpoint, or the computer vision is like machine learning for images is one way I like to think about that component of it. Yeah. And also image understanding is another way to think about computer vision, or the portion of it that's associated with machine learning and artificial intelligence.
Yeah, and there are other fields of AI, for example, natural language processing. That's another field where you deal with text data. We also have speech recognition, and that's another big field. For example, when you call Alexa, there is an artificial intelligence module that recognizes your voice, does the processing, interprets it, etc. So that's the speech processing. But among these different fields, I think computer vision has the biggest potential, because if you look at human visual system, it spends about 30% of its processing power on the visual part, because visual information is so rich. And we are also in a lucky spot that there are so many hundreds of millions of cameras in this world, which are continuously gathering data. So there is a lot of activity in the computer vision space. Right. Even in aerospace, for example, for military and other applications, there are a ton of applications.
I mean, everybody's mobile devices, right? Everybody's mobile devices have cameras. So there's all kinds of video and image processing taking place. Yeah.
Yeah, and it's going to transform multiple industries. We are going to see in manufacturing, we also do consulting work, and we see people are using computer vision in manufacturing, in agriculture, in security, obviously, in autonomous driving. That's a very big area. So computer vision is everywhere, and that's going to explode. It's already on the rise. There are so many jobs out there, and we will show you right there in the video. We will show you the pay grades of people who get jobs in this area. You can see that people make more than $1 million in companies like Facebook, etc. Of course, these are senior people, and these are level 6 engineers who are accomplished. They are at the cutting edge. But it gives you a sense of an engineer is making. This is not like an entrepreneur, or this is not like a senior manager. This is an AI engineer making that kind of money in big companies. So that gives you a sense of why it is worthwhile taking a very hard look at these emerging fields as a career option.
So what about some of the course offerings? You want to talk about some of those?
Yeah, sure. So basically, before even we go there, right, it's instructive to know what are the things that you need to learn to get into the field, and what are the libraries you need to learn. So the very first thing is that it's very important to be very good at coding some of these algorithms, right? Algorithms are building systems. So you should be a very good programmer first, because this is a very engineering oriented field. You need to be able to write code, and Python is a great place to start, but don't end there, right? Learn as much as possible. If you want to learn C++, if you need to learn C++, learn it, and because it expands your chances of getting a job. So, but let's start with Python, right? Suppose you have Python expertise. What do you need to learn to get a job? First of all, as I said, that OpenCV is a fundamental library. You have to have good expertise in using OpenCV. That's number one. And then there are two other libraries that are very important. One is PyTorch, and this is a deep learning framework from Facebook. It's open source. It was developed at Facebook. And the second one is TensorFlow and Keras. So this library is developed by Google, also open source. These are all very good libraries. And if you have mastery over these three libraries, and you have mastery over computer vision and deep learning techniques, I think there is no way in the world you will not get a job. It's very easy to get a job once you have these 2 or 3 things under your belt. So from our course point of view, Computer Vision 1 covers traditional computer vision applications and not so much deep learning. We show you how to use deep learning in applications, but we don't show you how to train deep learning models. Computer Vision 2 is all about applications, and there we go over many different applications. We don't even worry about which library you're choosing. We expose you to several libraries that will allow you to you just build your arsenal of techniques and libraries and tools that you can use to build real world applications. And the third course is deep learning with PyTorch, where you go over the fundamentals of deep learning. And it is taught using PyTorch. And by the end of this year, 2021, we will also launch deep learning with TensorFlow and Keras. So basically, it's all covered. Anything related to computer vision that involves deep learning, it's covered in these courses. We go over image classification, object detection, image segmentation, pose estimation, etc. But these are very meaty courses in the sense that we go over all the theoretical details. You will learn about what is backpropagation and things like that. So once you take these courses, I think it is equivalent to getting a master's in computer vision and machine learning. You will get that level of knowledge. In fact, I can very easily say that by the time I completed my master's, I did not have this knowledge that people gain by taking Computer Vision 1 and deep learning. Let's say, even if you take these two courses, Computer Vision 1 and deep learning with PyTorch, I did not have that knowledge after my master's, right? So, and I can say that without any hesitation. These are solid courses. We took the best from various things. We are also very industry oriented, right? We are very, very applications oriented. So we picked the topics that are actually used in the industry and left out the things that are only of theoretical importance.
Right. So what about the prerequisites? People might be wondering about what's actually required to get started, and maybe what are the potential learning tracks here with 3 or 4 courses that we offer?
Yeah, so the prerequisite is just, intermediate level of knowledge in the Python programming language. Once you have that, you don't need any other prerequisites. But if you're starting, you've never tried OpenCV, you're just starting out, I would suggest that take our first course, OpenCV for Beginners. And that is meant to be a quick, a very short and fun course. It is short, it is affordable, and it is something that you can try in a month. And that will give you an idea, do you actually enjoy building applications? Do you actually enjoy this field of computer vision and AI? Mm-hmm. And once you have completed that course and you're certain that you want to invest, time and energy into this field, then I would say that take Computer Vision 1, which is about classical computer vision. We also cover some deep learning, but it's very important to have the foundation ready. A lot of people I see, they directly jump into deep learning. That's also an option. But then what happens is that in real world, there are many problems that you don't solve using deep learning. It's just absurd to use that technique for solving some very easy problems in computer vision. And if you don't have that foundational stuff, you will try to look for a nail because you have this deep learning hammer.
Exactly.
Yeah. So, right. So that is a pitfall that people should avoid. So, Computer Vision 1 is the second one. You can also skip OpenCV for Beginners if you're convinced that, you want to commit 3 to 4 months. You can directly take Computer Vision 1. and then take deep learning with PyTorch. If you have more time to invest, let's say you're a student, then you should definitely take the whole, 4 courses, or at least start with computer vision 1, computer vision 2, deep learning with PyTorch, and then when deep learning with TensorFlow and Keras comes along, that is also going to be very useful.
So computer vision 2, there's must be a little bit overlap between computer vision 1 and computer vision 2, but computer vision 2 is more application focused.
Yeah.
Is it considered a little bit more advanced, or what are the prerequisites for that?
It's not advanced, but we don't dive into a lot of theory in that. We are more interested in teaching people about the tools, right? For example, if we cover something like a barcode or a QR code scanner, we will tell you, oh, this is the library, this is the best library to use for this application, but we may not go into how QR code is actually read, right? So we don't go into that level of detail. Similarly, we cover applications related to faces and face swapping and things like that. And in those cases, we go over some theory enough for you to understand, what's going on, but we may not go into the theoretical detail of, say, facial landmark detection, which can be mathematically challenging for people, right?
Right.
So yeah, so it is based on you build applications, right? That's the main focus. We will teach you how to build web applications, for example. So you get exposed to a wide variety of applications.
One thing that I noticed just in my own continued education in this area was that having a little bit of overlap is actually, I found it to be a valuable experience, because you might cover one particular topic in a class and then hit it again in another class, maybe from a slightly different perspective, or just the passage of time, and you're looking at the same topic again, several months later from a slightly different vantage point. I found is actually very helpful. So
actually, that's true about our deep learning with PyTorch and deep learning with TensorFlow courses as well. You may ask, if I have taken deep learning with PyTorch, does it make sense for me to take deep learning with TensorFlow as well? And the short answer is yes, absolutely. TensorFlow is the most popular deep learning library in the world, and PyTorch is the one that is rising the fastest. A lot of people like using PyTorch because it's very Pythonic. For Python developers, the learning curve is it's very gentle. You can easily pick up PyTorch. But when you go to the industry, right, you're looking for a job, right? You want to offer the best things you have. You cannot say, PyTorch is the library of my choice, I don't work in TensorFlow. Then people are not going to hire you, the people who actually use TensorFlow. As engineers, we should not be married to the tools, right? We are there to solve problems. And if taking this course, deep learning with TensorFlow, the theory is already covered in deep learning with PyTorch also. So there will be an overlap and there will be a repetition, but it will be in the context of a new course, right? So you are actually looking at from a different framework, right? TensorFlow is a different framework, and we are also adding new applications so that there is you get different applications with these 2 courses. But with, let's say, 30% extra effort, you learn a new framework, right? And now you have covered everything. With PyTorch and TensorFlow, you are all set in deep learning. And you also know the theory from, when you take either course, we cover the theory that is necessary. So I think that what you said, it also is a revision of your theory when you take the second course. And people should not be married to tools. And I say this about other Python and C++ also. Python is definitely the first and the easiest language to get started with AI, but don't ignore C++ completely, because when you go to the job market, you may find that there are equal number of jobs in 2 areas, right? And you've already learned, you've done the hard work of learning the basics, the foundation, and now you're just worried about, I don't like this language or that language is hard. Language is just a way of solving problems, right? We should not be married to one particular language, because as engineers, we want to see ourselves as problem solvers, and whatever is the right tool for the problem, we'll use that, right? And two of our courses, Computer Vision 1 and Computer Vision 2, they are offered in both languages. In fact, when you purchase one course, the other course is for free, right? So now you can actually compare code side by side to see, oh, this is how it is done in C++ version of OpenCV. So
That's really great.
another huge advantage.
I like that feature especially. I think that's great. So we talked about Python versus C++ earlier, but I think some people might be wondering, obviously both would be good to have under your belt, but some people might be wondering to what extent is either language used in industry? And if you only knew one language very well, or you had an affinity for one of those languages for whatever reason, what is the market share for that language in industry?
Yeah, so Python is definitely, it is fast becoming the language of scientific computing. But then, there is, you can easily learn the concepts using Python, and it will also be, there are several jobs, there are large, I would say 50% of the jobs would easily take somebody who has Python skills. But then there is this whole other world of embedded computer vision, for example, where you're trying to do computer vision on really not very powerful devices, right? You're not using a GPU. Even if you're using a GPU, it's like an embedded GPU or something. In those cases, a lot of times these algorithms are implemented in C++, right? And sometimes even in C, right? In C, so that because you don't have access to that much computational power. And that's a lot of, that's also a very big market. Think about all the security cameras, all kinds of devices which are embedded. I mean, if you love one language, Python is great. Try Python. You will gradually learn C++ over time. What I want to emphasize is that don't think that you're a Python developer only, right? Think about yourself as an engineer, and you will learn and whatever needs to be learned to make yourself fit for the job market.
All right. So, one thing people might be wondering is there's certainly a lot of freely available course material on the internet. Universities are offering all their many top universities are offering many of their courses online for free. There's lots of tutorials. How do people sort this out? And what do your courses provide that maybe is not available online for free?
Yeah, so I actually encourage people to look at all the free stuff first, right? Because it builds their confidence, it builds the momentum. They start knowing what to expect, what they want to learn. So they start having an expectation what they want to learn. So by all means, there are a lot of free tutorials on opencv.org and also on learnopencv.com. Go ahead and try those. And there are several other very good bloggers also who you can try. And then there are free courses by universities as well. Try those as well. But then at some point, if you feel that you're missing a structure, sometimes what happens is that you take all these pieces, but you don't get a bigger picture. Pieces of computer vision, but you're not confident enough to go and present yourself in front of a job interviewer because that you have learned in bits and pieces. You have not connected the dots completely. And that can be a blow to your confidence, right? When you take a course, it is structured and that the important things have been covered. And suppose the interviewer asks you something which is beyond what you have learned, you can confidently say that, oh, I have not learned that, that's okay. But I know this thing. I have gone through a structured path to learn all these things. And in our courses, we also cover, there's a lot of code that people go through. You write a lot of code. I was saying that you need to be very good at programming. So you need to write a lot of code. You read a lot of code. So that's a very good practice. We also give you assignments and projects, and together that creates, a sense of urgency. It creates a sense of responsibility that you have to finish this thing. What happens with online material is that you take this and you read the code, but you never write any code, right? You feel that you have understood it, but if you take away that code, you cannot ever write from scratch, right? You use that material as a crutch. So when you start doing something like a project, etc., it actually comes together, right? You feel you need to, job market, it's basically a confidence game. You need to have your expertise to a level where you're confident you can face an interviewer, right? And then we also, not only that, on the internet, in a blog format, it is simply not possible to cover things in depth, right? So a lot of times people gloss over things, and we do that ourselves also. It's just simply not possible to go in a blog format. You have to condense everything to be easily consumable. You don't have that user for an hour, right? So you have to make sure that they learn whatever they want to learn in 10 minutes. And in doing so, the medium is restricted in some sense. So in courses, we don't have that restriction. We know that people are committed, they are ready to spend time on this. And so we take the time to explain in depth. That's a very important thing as well. And there is also peer pressure. When you see that other people are, asking questions in the course forum, they are enjoying the course, it puts a little bit of pressure on you in a positive way, which propels you that I also want to do something.
Well, you're all in it together, right?
Yeah,
it's a little bit of camaraderie too. And I think you said it perfectly, that confidence comes from mastery.
Yeah.
So you feel confident when you know that you've mastered one particular topic.
Yeah.
And then the other thing that you brought up is doing projects. So actually executing a project and taking what you've learned to create, an extension of that is, I think, very valuable, very rewarding. And also it forces you not to skip steps. So you could be reading a blog or watching a video online and nodding your head, yes, this all makes sense. But when it comes time to actually code something or create something a little bit different than what you learned, if you actually have to program it and get your hands dirty, it forces you not to skip steps or gloss over details that are actually required. So
right.
I think that's a very valuable experience. So let's talk a little bit about what sort of jobs are available in industry. I mean, some immediate ones come to mind: the entertainment industry, perhaps medical imaging, manufacturing. But what are the different domains and types of fields where computer vision is actually being used more recently?
So Professor Andrew Ng, who is also the founder of Coursera, he likes to say that AI is like electricity. So when electricity was invented, it was used for lighting purposes. But within a few years, it transformed multiple industries. It was used in manufacturing, in agriculture, and a lot of different things. And AI has the same power, right? It is used in certain industries right now, but it is transforming multiple industries, including manufacturing, automotive, autonomous driving cars, and agriculture. We have a lot of people who are working on pest control, who are working on removing weeds in an agricultural setting. Medical imaging is huge because now AI is doing better than radiologists in some sections, right? Because when the data becomes available and it's a repetition, some tasks which are repetitive, in those cases, AI is going to do better than humans over time as the data becomes available. It is those creative fields, let's say even in music and generating new images, AI is learning from existing data and creating new art form, right? But there are certain fields where AI is not going to take over. For example, comedy is one example. Comedy is you cannot train on comedy. If you look at the jokes that are produced by an AI system, they're usually pretty lame. They try to rhyme something because for creating comedy, you need things that's not in a specific area. You could tell a joke which combines something going on in the music industry with something that is going on in sports. And when you put them together, it is funny, right?
Right. It's really hard how do you quantify that, right?
Right. And it's not domain specific because you took something very different in a completely different domain and combined it with something very different. And so those kinds of things which are one-off, right? And it's even best comedians do not know what will fly, right? So they do a lot of tests themselves.
Right.
So those kinds of fields are very difficult, for AI. But everywhere else where it is very structured, like manufacturing, it's a very structured environment. Warehouses, it's a very structured environment.
A very controlled environment, right? So
yes.
a lot of variation is removed in those cases, so which makes it easier.
A lot of variations are removed, and they are repetitive tasks that can generate a lot of data, right? the key thing is that they are repetitive tasks. The same task is happening over and over again. No matter how complex the task, you can put a camera there and get as much data as possible as you want, and ultimately that problem will be solved, right? So, I mean, if you look at all the companies, who are the companies hiring? When I graduated back in 2006, I had a few options. I could go to Microsoft Research, I could go to Google, I could go to a few different places. But now the people who come to us for consulting, they are all over the place. Obviously, these big companies are still there: Microsoft, Google, Facebook, Adobe. All these companies are still there who hire computer vision research engineers. But then there are small companies, one or like 5 people companies who are working on something very specific that you may not have thought about, but they need computer vision expertise. For example, one of the first consulting projects I did, they were sorting Lego pieces. So these Lego pieces, there are 10,000 of those. We don't realize it, but there are 10,000 unique Lego pieces, and they wanted to identify with reliability which piece it is, right? So because they wanted a replacement system, that if some piece is lost, they can replace it. So you can see that that is something that came out of the blue. I had never thought about, oh, that's an application area of computer vision, right? Another one was there is a company that is using computer vision for detecting the species of fish when they have, when they catch fish. They want to make sure just to, what is the size of the fish, what is the size, what is the species that they have caught, and things like that. So to do that analysis, they are using computer vision. Microscopy companies, we have worked on so many different applications, even applications which have a huge impact, like one where they were identifying shooters in school. And we had worked on a very proof of concept project with a company. And recently, a few weeks back, I came to know that they have grown into a full-fledged company and they are offering the service, right? So my point is that computer vision is everywhere. It's not just focused on these large companies, but I just gave you several examples. I'll add one more example. There is a company that used us for detecting fraud in fashion merchandise, like bags. These bags are very expensive. Some of them are $2,000 for a small bag by a recognized brand. And they want to protect the brand identity. So they want to, something that is $2,000, you can make a very good copy of that for $1,000, right? And then sell it for $1,200 and still make a very good profit. So, but fortunately, these companies have very high standards, trained a machine learning algorithm to know the difference between a fraud, a bag, and the real bag. So you can see now in the fashion industry, we have worked, and this is a small company, I'm talking about a consulting company with 40, 50 people. We are receiving such a diverse set of problems to work on. We worked on sports analytics also, where we are tracking soccer ball in a sports setting. There are other companies who have approached us for baseball, for golf, and other projects like that one. So it's a very diverse range. We are lucky to be in this in this position. Where
I'm really curious that the example that you pointed to with the counterfeit merchandise, was that machine learning only, or did that incorporate deep learning?
It was a deep learning project.
It
was a deep learning project. And this company basically is in the business of selling secondhand. They buy these handbags and then resell them. So when they buy these handbags from people, they have to make sure that these handbags are genuine. And they have experts who go and check whether these things are genuine or not. And that requires a lot of expertise, right? Even to give a quote for this handbag, how much should it be quoted? You need to know the exact make and the model of the handbag, which is, there are 10,000 of these again, right? So you have to automatically determine, at least to get a ballpark, which kind of handbag it is. Otherwise, there are these experts who are, tens of experts who are employed just to look at these images and make sure that, oh, this is this kind of handbag, right? This is a Gucci handbag of such and such model, and therefore it should be priced at such and such, right? And then the handbags comes in, and you have to determine whether it is counterfeit or not. And that requires a different level of expertise altogether, because mistakes can be really very expensive.
Right.
Yeah.
Right.
They are putting their name on that this is a genuine item.
So we've covered quite a bit in this discussion today, and just curious if you had any final thoughts for people who are perhaps on the fence about getting into computer vision, or wondering exactly, how they might start.
Yeah. So final thoughts. First of all, don't be afraid of taking a leap into this field. The job opportunities are tremendous. It's a very good career switch for people who are interested. The first thing you have to answer for yourself is, are you interested in computer vision and AI? And if it, sparks joy in you, then this field is full of opportunities, high paying jobs, etc. And take any learning path, right? It's not necessary that you take our courses, which you can, but jump into this learning path. Try to learn as much as possible from free material. And when you're ready, come to our courses. But even if you don't, it doesn't matter, right? The main important thing is that you embark on this journey, knowing that there are a lot of jobs available in this area. And if you spend about 6 months to about a year and dedicate your time and energy into this, you can become an expert, an engineer who can create, who can join this AI revolution. So with that in mind, I wish you all the best. Welcome to the AI revolution.